And we are now live streaming. Hello, everybody, for the live stream. Okay, so let's go back to this. So I am not sure, have you tried running the script? Well, so this is also being recorded, and you can ask questions as you have them. So if you try to run the script and run into some problem, just ask. You can unmute and ask. Let's go back to this. So what I'm going to do here is to generate a make file for the launcher. I'm going to place it in the parent build directory, and to generate it with debug information. Okay, so let's do this. And now we are going to get into Ines is telling me that people cannot unmute themselves. I think that I activated that. If you want, you might try and ask questions or say something or tell me if it doesn't work. Okay, we are here. We got a make file. So we just make it. And finally, execute BDMR and pass it the B kernel. And it didn't crash, which is a good sign. Echo the result of the last execution, and this is 3. Why is 3? Because it returned the small integer 1. I guess that many of you already imagined it. So what does this kernel do? Let's see.
Hang on, Pocho.
Yeah.
Juan is saying that he is having problems.
Okay, so let me check that. Let's go back. Yeah. I will stop sharing again.
Maybe Juan can tell what are the problems.
I believe the worst problem is he cannot talk.
Okay, so
I just unmuted you.
Yeah, but so okay. You are all unmuted, but
yes. Thank you. Now I can talk. Okay, please give me.
Yeah, that's it for me.
When everybody has a microphone, we need to be able to mute ourselves so we don't introduce noise, and to unmute ourselves each time we need. And please, Pocho, wait a little bit, because fighting with this mute and complaining about this meant I lost most of the last things you did. Okay, I did the first time, was trying to follow, and when you ask, is anybody following? At that moment, I could not do anything more but try to talk. So please go a little bit slower and wait for people to tell you we are following. Okay, no, I will try to mute and unmute and see if this works. Sorry to click on this, but it's very necessary.
Yeah, calm down.
Yeah, also, I think the binary is not being generated.
Okay, perfect.
And now I am unmute. It works. Thank you so much.
Thank you, too.
Well, we are all trying to learn how to use Zoom.
Yeah, sorry, Juan, could you mute and unmute again?
Yes, now I am mute. No, the other way. Now I am unmute.
Okay, perfect. No, because here I have an option that says allow participants to unmute themselves. I put that on, but it didn't work until I unmuted everyone. So sorry for that.
Okay, cool. So I got to the point of cloning the repo, CD PowerLang launcher, LS, and that was it for me. So
okay, so I'm going to paste now in the chat what I wrote.
Okay, cool. Thanks.
If this or
in the chat,
on the screen.
I paste the link to the script. So you can follow the script.
You have to, but you have to execute this on the launcher because this is not in the script.
Oh, sorry.
There. You have to be on this directory.
So I also wanted to talk, and I was on mute too. Yeah, but so I ran the script, but it did not generate the binary, right? So in the build, I have no binaries.
It didn't generate the binaries. This only creates a makefile in the build directory. And there you have to run make. So you go back
I'm doing
to
that.
the build.
Yeah, I have it done. Thanks.
And there you make it. All right, so are we all on the same page now? I will give you 2 minutes for that.
To run the command you just pasted, where do you need to be standing?
In launcher, PowerLang launcher.
And what should the result be?
You should have created a makefile in the parent build directory.
Okay, I got that. Done.
Okay, are we waiting for somebody else? I guess we are not. So I will continue.
No, hang on. I'm still downloading some stuff.
Okay.
Rossal thinks. Which directory do I want to be in when I run the CMake?
You want to be in PowerLang / launcher.
Okay. Okay, so I got an error. An assertion failed while building the nativizer.
While building the nativizer.
So it's not important because I don't have to I won't hold up other people, but I'll just post it for you. Okay.
Okay.
And then go on without me. Okay. So.
Okay.
No, I think it's important and part of the idea of the hackathon that
maybe you can share the screen and we can tell you what is going on.
Yeah.
All right, let's do that.
That we all have what we want to work with.
So this one. Right, so here it is building the nativizer. And then there's an assert failed here. Unfortunately,
Initialize nativizer.
It doesn't say what the assert fail is, which is annoying, but that's okay.
First question is, anybody else did it have this same error, or it went okay? Just want to be sure if it's just lag or what.
For me, it went okay.
So Elliot, could you try to run the script again and check whether it's just some random error? I don't know what this was, but I have random errors on the. No, okay, so let's do something different. CD into Powerland. I have some random errors on the CI when I run tests, so it wouldn't be strange that we have something there that's not okay. So let's try to do what the make file does, right? Check the make file here. We have some targets there. And
so host, yeah, and then build. So if I do a make -n, what target should I specify? Make -n all. Nope. But this is the.
Well, with Mac, there is actually another issue. I don't think the binary will run and load any code on a Mac.
Right. So let me be. You go do this in Linux, and I'll try and catch up at another time with a Linux VM. I think that's better because I'm holding people up.
Okay, well, maybe Elliot, you can be the Mac maintainer.
Yeah.
No, but this is we have a CI that runs on Mac and Windows too, but we are not testing the launcher yet, so that might be the reason why this doesn't work there. Okay.
Now the issue is that on the Mac you cannot map anything into the lower 4 gigabytes of an address space.
Oh yeah.
Therefore, you won't fit into the 32-bit pointer, and the class has only a 32-bit. You know,
there is a way of doing that on Big Sur. I was reading about that just the other day. I'll try and look that up. There is.
Yeah, well, I don't have a Mac, so I don't have experience. I just know that for the talk in last year on Smalltalks, we had to introduce some hack in a sense of compressed pointers with a base offset to get it running on Boris' Mac. So just setting the expectation, right? Nothing more.
Yeah.
Well, if it's okay, then we shall continue. Can you see my screen? No.
We can see only you.
There. Do you see me now?
Yes, yeah, no, now we see your screen.
Okay, perfect. Then, okay, so where we were. We just ran the launcher. It loaded the BSL, which is the image segment, and executed something. So to understand what it executed, just let's go to the B source and see the code, or maybe less. So each module shall have, well, we are trying to support modules. We are still not there, so we only have one module, which is the kernel. But we expect that each module should have a class defined that specifies the initialization steps for the module. And in this case, we have kernel.st, which specifies the kernel module. And it has only an instance variable here, the runtime, which is what we are going to give to the launcher to let the launcher execute code inside the image segment. It will provide a callback to the launcher. There we have the Bootstrap initialization code. This is executed by the virtual Smalltalk runtime. So this is executed actually before the image segment is generated. It creates all the contents so that then you can generate or compile all the Smalltalk methods from the bootstrapper. You also declare the globals that your module is going to have. And finally, you have an entry point. So this entry point has a callback tag, primitive tag here, which will let the nativizer know that this has to have some special ABI so that you can call it from C. Actually, when you execute this, you don't really have a kernel instance. We should have, but in the state it is now, you don't really have a kernel instance, so you cannot just say self foo. You just have to create the instance and send it the message. And finally, we have this foo method, which calculates 42 factorial and checks whether the result is okay or not, and returns that. So what we get from this foo method is what is getting sent back to the C launcher. So the reason why we got 3 instead of 1 is because small integers are tagged. So 1 in native machine registers is represented as a 3. And well, that's what we have just executed. And maybe you want to see more code in Smalltalk. For doing that, we can go to the bootstrapper and execute. If you have a look, we went to powerlang/bootstrap, and there we execute Faro UI bootstrap.image, and there we have a Faro environment. So here you can browse. Well, you have different things to browse, but let's open a class browser. No, this is not the class browser I wanted to. This is the class browser for vcode. We are seeing here vcode in a ring environment, as I showed yesterday. But I wanted to open a Faro class browser. And here we can filter Powerlang. And we have all the code of the bootstrapper in Faro. So we have the JIT compiler, we have a parser for assembly. Actually, this is just the assembler. the assembler for the JIT. There is an assembler for Intel. Here in nativization, you have the JIT compiler. You have the opcodes here, which are the ones that I showed yesterday, where you have more of an AST, and you also have some kind of optimization, which are when you send a message, you can encode in the message sent some optimization so that you put things in registers in a better way, because traversing the AST or the S expressions of the AST can lead to some not that efficient code. So you can, when you are compiling, you can add optimizations there.
Pocho,
So-
can you show me what's in metaphysics and mirrors briefly?
Okay, this is a little bit what will I say for this? This is a little bit old, and it's very interesting, but it's not that well supported right now. What metaphysics has is an API for working with remote objects. Okay, so that this is something that we used in the past and that I want to make up to date, but I didn't have time. So you can have different runtimes with different object formats. Everything is configurable, or should be. Different storages, and you just connect to a remote runtime, and you can find some objects through the bridge, get handles to those objects. Those objects could even be in your local runtime if they are wrapped correctly. You can send messages or just analyze them. But this is not really, or I'm not sure whether this works or not. Probably it's not working. So what else do we have? Let's see. Here we have the S compiler is the Smalltalk compiler living in the Faro image. This is the one that will compile everything into scompile methods. An scompile method has the same shape that it will have in the bootstrapped environment. So this mimics exactly what we have in the specification of compile method in the vspecs. And but we are using it for the bootstrap process. And well, finally, let's see a little bit more. The expressions. Let me check where they are. Here. So when you compile a method, you get an AST, and that AST gets brought into some binary or some encoding in arrays, nested arrays with codes, and then you can decode that and you get these expressions. So this expression hierarchy is very similar to what you get in the AST node hierarchy, but it shall be a little bit more efficient. It doesn't have the names of the things. For example, if you access a variable, then what you will get is an identifier. The identifier has a binding, and the binding can be of many different types. And if it's, for example, let's say an instance variable, you only get the index of that binding, right? If it's a temporary or an argument, if it's a temporary, you just get the position and the index of the environment where it is stored. If it's an argument, it could also be inlined. and that's it. So here what you get is mostly numbers. So when you want to use this, you have to do it within some environment or some nativizer, some whatever. So what what you are going to do is to tell the evaluator to do something with this bind. Let's check a little bit more here what we have. We have also the O compiler, which is an optimizing compiler for some special code that we want to optimize. This one generates a different IR. This IR is more similar to a low-level IR, where you have values. Every value in this compiler is a Smalltalk object, so you cannot really have, for instance, a value of type native integer. You have to take some object that you assume an integer, a small integer, and change it. But well, I won't talk too much about this one because it could take me much more time. Just to know that it's there and it's what's used, for example, for generating the native code of the right barrier or the lookup, things like that, that need to be a little bit more efficient. And it has some passes there to do transformations, like checking the control flow graph or converting to SSA. And finally, in building, we have the image segment writer, which is the one we use to generate the image. And in the emulation package, we have the virtual Smalltalk image, which is what we use to generate first all the classes and the main objects, and then the runtime, which is what we use when we want to do something more fancy than just generating objects by hand. We can send messages here, and it will create an evaluator and use the spec to evaluate whatever message you send to the receiver. This is more or less what we have. We have failing tests here are the ones things that are not working yet, and here we have the ones that should pass. We will see. Well, this will take some time. So while these tests run, please ask questions.
I have a question. You are running Faro on the top of Cog virtual machine.
Yes.
Right now.
Yes. We are running. Okay, let's start. We are running this VirtualBox virtual machine, and then just to have some fun, we are running this VirtualBox virtual machine where we have this virtual machine for Faro, where we are going to generate the virtual machine by the usage of a virtual Smalltalk runtime. So yes, we have different virtual machines here, and it can get confusing. So it's a very good question. So here, this Faro virtual machine is going to generate a file. I'm going to show it to you.
You are going to generate another virtual machine.
Yeah, exactly, yes.
And this virtual machine for Faro, or has to be with B Smalltalk?
No, this one has to be with B Smalltalk, and actually includes everything. It includes both the the virtual machine and the image in the same thing. So what we are generating here in this BDMR BSL, this includes an image segment that also has the code that is required to run this same image, to send the messages and things like that. So I'm going to show one more thing, if I can find the Faro, which I don't know where it is. Okay, most tests passed. A few didn't pass. Okay. Wow. Who knows what this is? I am not sure, so we'll leave it for later. Maybe well, when we have some free time, we will see. But so what do we do?
May I have a question here?
Yeah.
Why do you need a Faro anyways? Why the B Smalltalk cannot be started by itself? What's the inner motivation?
Well, because if we want to let people to bootstrap themselves, then they either need a working B or some other Smalltalk, right?
Well, you can think of Faro here as like, for example, Eclipse if you do Java, right? That's just an IDE for us.
Okay. I see. I see. Okay. So you don't have a working IDE for B, so you decided to take Faro as, let's say, working IDE and make it working, and then later on you will switch to B IDE.
Yes.
Yeah. Okay.
Yes.
As soon as we can, we will switch for sure.
Great. So what's happening with like, for example, using Quiz or Squeak as the environment?
Yeah, we
Nobody's
could
interested
also
in
do
that.
that. It's
Well,
just
no,
that
from my perspective, the situation is really tragic because there are different parts that I do, and I'm forced to do some of them in Squeak, others of them in Faro, and some of them in Quiz, and some of them in Smalltalk X, because there are certain things that are simply broken in whatever particular dialect and unbroken in the other dialect, but there are some other things where the situation is exactly the opposite. So it's just there's no dialect, not that I'm interested in particular dialects of Smalltalk 80, because what I'm doing is Smalltalk 25, which has nothing to do. But there are two sides to that, right? Well, one is that we cannot exchange code, and this is really, this is really a situation that we have to do something about, but nobody really knows what, right?
Well, yeah, okay. I won't go into a rant, but there used to be no problem. There is an attempt to get Tunnel working on Squeak. There was some movement to get Tunnel. I mean, the Vast people and the Gemstone people have pushed.
Go there.
Let's not go there.
Yeah, let's not go there for now. Yeah.
okay. Let me show a little bit how this thing is getting to work. This is a test that generates a kernel, right? It's not the same kernel, well, not the same file, but it's the same kernel. So I'm going to put a halt on this test and see how it works. Well, I should have run it before. It takes like 10 seconds. What we will see is that we have a builder with all the Smalltalk classes and all the Smalltalk methods. This is done by field classes. or before that. And then what we have here are two things. First, we are going to nativize all the methods, and that means generating native code ahead of time, so that those methods don't require a JIT compiler or an interpreter. And then we are just going to put what we got inside the image segment and write the file. Okay. So the interesting part is this nativize for DMR. So it's DMR for dynamic metacircular runtime, which is the runtime that doesn't require a separate VM because the code is nativized ahead of time. Okay, we are going to use this object. And this is the important part, nativize. And okay, so it has to do some steps. The last one is to nativize the methods, right? To get some method and emit native code for it, and then the other, and the same, and same, and same. But we also have to do some stuff before that. One of them is to initialize the ahead of time compiler. This is the one that will do that. And we also have to initialize the objects that represent sense, because, well, actually not the objects, but the class, because it needs some special objects generated by the nativizer. So this nativization environment has some stuff. First of all, it has some globals. Well, actually, they are not really globals. They are things used frequently by the native code, like, for example, the lookup native code or the invoke native code for methods that are invoked. And you could have the save point check here too, and some other stuff. So, and the right barrier. So we are going to generate an array that has the pointers to all those objects, right? So for example, the small integer behavior or class, if you will, we can later talk about what the objects in B point to in their meta slot. But okay, we are going to use the small integer behavior, and we are going to put it on this array. We are going to create a placeholder for what we've put in lookup, and we are going to put a placeholder for each of these elements, and we are going to store them in this array. So I'm going to just get out of this. And let's inspect the nativizer. So here we see globals, and we have the small integer behavior, right? If you see, this is a slot object map. It's a map. It's an object that is going to live in the image segment, and the others are the placeholders for the lookup and everything else. So when the nativizer has to emit, for example, lookup, yeah.
I'm sorry for interrupting you, but we are an hour in, and I'm afraid this is turning into another show and tell session.
Yeah,
so,
you are.
Yeah,
I wonder how to.
Can we really get to something resembling hacking?
Okay.
This has nothing to do with setting up B.
No, it's not. So what I can suggest is that if you want to explore the code for the nativization, we have it here, right? And in the bootstrapper.
Yeah, we will be exploring it in a few minutes.
And we will be exploring it in a few minutes.
So people will actually see it.
Yes. So just, well, we can stop here. And let's do some hacking. Right? So I invite you, Boris or Jan or Elliot or whoever wants, and just share your screen and start hacking.
No, Pocho. I will lead you. You will be driving, right? Because the thin shell is gonna be running on your Pi, right?
Okay.
Is it powered up?
I have to set up the thing near me, but yes.
Okay. So before, no, don't go away. Before we start that, can you share your screen?
Okay.
Open a workspace. Actually, no. Yeah, go to Iceberg, close that.
Do we want to use this PowerLang or the other PowerLang?
There is, which one is this? Well, what is the difference?
This is the one without the debug.
I don't even understand what the difference is.
What is the difference, Jan?
Well, the difference is that mine is cloned from my fork, which has the debugging support. I wrote, so we have some.
Oh, no. We want a remote that is the PowerLang, because I just pushed the beginning of the VM Hackathon branch.
Okay.
Yeah.
So
This is what is the remote from which this was cloned. This is PowerLang/PowerLang, right?
this is
This
PowerLang / PowerLang.
Okay, perfect. So go to Iceberg.
Okay.
That's in tools. Yeah. Pool. Yeah, that one. Fetch.
Can you see something else?
Well, we are not. How come we're not seeing anything?
Not sure. Did you push?
Do
you push to this repo?
To this repo, but not to master.
Maybe I have to do something else,
Okay.
like, I don't know.
Click, yeah. And we want VM Hackathon. Just 2 commits ahead of where master is now. Which is just simply cherry pick of those 2 things we did in July.
Okay.
Perfect.
Well, okay, there we are.
Okay, so now we have the latest B to start, or PowerLang to start working with. Now I want all of my stuff in here.
Okay, so.
And that may take a while because the open Smalltalk VM repo is kind of huge. The easiest way to do this is let me share the link. So okay, where is the chat? Here's the chat. And okay, go there, and on that page there is 1 line of Smalltalk code that you have to execute in a workspace. Yeah. Mm-hmm. Right. This is going to take a little while, and while it is doing this, you may want to grab your Pi.
Okay.
What is it catching now? Fetching now?
This is all Elliot stuff that when it will try to load the baseline, it is going to pull all my stuff.
I see.
Okay, while it's loading, then maybe if anyone is interested in GDB, then maybe we can break out and I can start showing stuff. If not, that's fine, because then I won't miss this one. But I kind of promised, so if there is strong interest, then maybe we can do that.
Yeah, you see the problem. I am kind of very strongly interested in your stuff, so it has this. These two sessions have to be one after the other. There's no way around like how to parallelize them.
I mean, everything is fine. I just don't want to disappoint people, because I kind of promised. But I mean, if we skip it, it's fine with me too.
Maybe we could use then the VDB when we hit some obstacle here, and we can use it in real life situation.
Well, one of the things that I wanted to do, and I said about this yesterday, is that we have I have here a very primitive replacement that I still don't have, and I want to replace it with VDB, because there is ULD, which is the processor perspective, but then there is the perspective which looks at the status of the target Smalltalk under debug, and I just had to have it, because otherwise it's very slow trying to understand what is wrong at a higher level in the target VM. But it's a really primitive thing.
Okay, then we could kind of work on that. If you have something you want to replace, and we can see the process how to do it.
Yeah, that's why I would like Jan to be in the set, that these two sessions, that they're in the same room.
Fine with me, but it seems to me that 4 hours is not long enough. But we'll see. We'll see.
Well, then we can do it to be continued.
Sure.
Okay, people. Did this load?
Yeah, this is slow. Yeah, it's very slow.
But I think it's on, right? No, or not?
It is working. It is thinking. It's not done yet. It's the same problem on mine. You know, it looks like it's completely frozen, but it's actually working.
Maybe it will crash in a few moments. Maybe you can show us top to see if it is somehow doing something.
I see that it's using the CPU.
Okay.
So yes, it's running.
Yeah, I did try to investigate. Back when I was trying to investigate what it's doing, it's actually an external Git process.
So external Git process is kind of loading into the Faro image, or
It's not even come to loading it yet. What it's doing is just finishing what is it, cloning.
I see. Okay. So it can be painful for Faro.
Ah, okay. So it's pulling my stuff.
Nearly there.
Yeah, I think it's almost there. Mhm.
Well, it has to do everything in one thread, if I'm right. So that is why.
And there it is, I think, because it's...
This is done. Yeah, you may
Yeah.
want to say, yeah, you may want to save your image now.
Yeah.
So that we don't have to redo in case things crash. Perfect. So next thing, there is one extra step in setting this up is if you go to the terminal and you go to actually the same terminal where you launched this and like open another one in the same, yeah, go to the Bootstrap. Right, and in there is Faro local, and in there is iceberg and local iceberg. Okay, yeah, Shingarov, and then in there is Faro-archc. Okay, go there, and then execute that get-pdls. Yeah, okay, perfect. So these are all the processor models.
Okay.
Now, yeah, you can close this. And then on that GitHub page that I posted the whatever, right, there is another, there's a couple of lines that will post in, do some post initialization of things.
This one.
Yes, do that.
Done.
Okay. Perfect. So now if you double click on that ArchCOPAL test and hit Control B to browse it, you will, okay, perfect. It all worked. Look, you see those little things?
There we are.
Okay. So
Yeah.
So these are assembler generators. So if you click on any of them, so you see this is the end if greater and store flags between A1, and stack pointer. And if you hit Control I to expect the actual compiled method, you will see it's the actual machine code that is generated. You see, in literal 2, yeah, there's a bit vector, and it's 1. So it's 1, no, 1 up, yeah. Right. So there is one instruction, and its machine code is that.
Good. So
Okay.
here.
So
That is nice.
all of this has worked.
You show me
And
what
it has,
like when the
it
instructions.
has no valves.
Ah, okay. This is a different thing. So this is never mind. Sorry.
Oops.
Now, actually, Elliot, maybe if you say this is a different thing, let's go to COG. So in the browser, go find class and find COG Power Compiler. Yeah, this one or the other one, whatever.
Well, Boris, wouldn't it be easier when you open your image just to show and share?
No, but it has in Pocho's image. I just want to make sure that people really can follow.
How do we find the class?
Just find class, capital C, little o g, cog, big P, power, cog, power compiler. There is, yeah. Okay, that's all the JIT. And if you go to any of the concretized categories, for example, concretized arithmetic, now Elliot is going to become really happy because this is stuff that he... Oh, okay. No. Wait a sec.
Yeah, this is exactly what I want to have a look at, and I want to.
Yes, but it has not compiled because it loaded it before we before we cloned the ISA definition of PowerPC. So go to the playground and say COG Power Compiler recompile. Yeah. Execute that.
Yeah, it's on.
And then click away and re-click back.
Yeah.
No, that's still not. Click away from COG Power Compiler.
Okay.
Still not there. I don't know. Close this browser and close this browser and in this other browser where it is ArchCOPAL test or whatever. Yeah, go find COG Power Compiler again. Yeah, it's in JIT. Yeah. COG Power Compiler.
There it is.
Much better. Yes. Now we've compiled it to actual machine code. And let me show you something. So the operands are constant and R of this add CWR. And if you click or if you press Control I to inspect the actual method, right, you see literal 8. is now has now 2 machine instructions, and it's a concatenation of a bunch of bit vectors.
So can you inspect one of those? And what's the class hierarchy of these guys?
Of the bit vector, it's an opaque external pointer to a Z3 to some memory inside the Microsoft theorem prover.
How do you know those instructions are correct? Do you have tests for that, or?
Because they come from a formal specification.
Okay.
That's assumed to be correct.
They are correct by construction.
Okay, thank you.
So if you compare them,
even the HCPDL is correct, which
well, yeah, I mean,
it's
if you
not always
start
the
from the wrong definition of the processor, well, then pray, Mr. Babbage, if I feed the machine with the wrong answers, with the wrong questions, will correct answers come out? Well, obviously not.
So the thing to understand here is that in the traditional cog, these concretized routines are written manually, and they are error prone, and you get correctness by, for example, testing the disassembly of the various forms, and then eventually by having a functional image under the simulator. What's happening here is completely different. We're taking a formal specification of a processor, which comes out of a design process, which gives us lots of assurance about the correctness of that specification, and then we're auto-generating the form of the concretizer. So the other thing to understand here is that COG has an abstract machine. This is Peter Deutsch's idea that was in HPS. So the idea is to define an abstract machine which is mostly 2-register but has some 3-register extensions. It's kind of RISC-like. It's halfway between a RISC and a CISC, so there's a very limited number of memory reads and memory writes. And then there isn't a formal specification, but there is a specification of the expected behavior. And this abstract machine is what we generate instructions for. So as you JIT, you create a series of these abstract instructions for this abstract machine. And then later on, when you come to generate actual machine code, the instructions of the abstract machine are mapped by these concrete methods into some number of instructions in the actual machine code of the actual processor. So typically it's a one-to-one mapping, right? So if it's add register to register, that will translate into, one abstract instruction will translate into one concrete instruction. But if it's complicated, then you may get up to say 4 machine instructions for something like a multiply, where you're also having to do special stuff to do with detecting overflow, etc., or whatever. What we want,
let me provide a little bit more here, because we are looking at the perfect screen here explaining this, right? So this is a RISC processor. So on a RISC processor, because of the prefetching, you are forced to have all instructions to be of the same length. And here, all instructions are 32 bits. So if you are trying to add in this case, you're trying to add an integer constant to the contents of a register. But if you have too many bits, they will simply not fit. So here you are adding a 32-bit constant, but 32-bit obviously cannot fit in an immediate field of a RISC instruction. So here we are first adding the upper 16 bit and then the lower 16 bit.
And why don't you take us down to a multiply? Look at say concretize mul RR.
Yeah, it's slightly down. Yeah.
There you go.
Yes.
Right. Ah, right. And so you see, this is implementation in progress, right? Because on most RISC processors, if you think about generating overflow from an add, a subtract, or a bit shift, there's kind of a 1-bit carry. So you only have to set one transistor. But with multiply, if you multiply 32 by 32, you get a 64-bit result. So there are essentially
and actually this instruction here is correct. If you make that thing a bit bigger, you will see in the comment that gem5 has a bug. So and actually I fixed the bug. So this is now correct. This comment about being bogus is not. It should no. It should be mul WO dot instead of just W dot. But don't change it as just yet. Let it be as it is now. But there is something much worse going on here. If you look at add RR, that is actually add RR. Well, something very bad is going on here because this sets flags, but the flags registers is 8 set of 4 bits.
Yes.
And different bits mean different things in different circumstances. So you don't have a carry flag and then or let's say okay, well, what would be greater than, less than, right? So on ARM you have greater and less, and then you have above and under, right? So these are signed versus unsigned versions of the greater and less flags. But on PowerPC, you kind of have now. This is on processors with flag registers. Now then, there are processors with no flag registers, like MIPS and RISC-V. And on MIPS we do this notice notice condition or something like that. And this is much worse because this is somewhere in between MIPS and ARM, where you have flags, but the flags registers is short, and you repurpose those bits depending on what you want. So in this case, the add, because it by default is an arithmetic instruction, the flag that it's gonna generate, that it's gonna put into the condition register is gonna be the signed version. But you have an unsigned version of this instruction that will generate into the same storage inside the processor, but it's gonna generate the unsigned version of the flag. So this is not implemented.
Yeah.
This is in progress.
Yeah, but Boris, it's straightforward, right? Because Ryan did it with the MIPS. The question is it worth generalizing the abstract machine so that you don't have to push the MIPS and power into the same kind of constraints? because one of the major differences in system architectures between RISCs and CISCs is that the call instruction on a RISC will load a link register, as it's called, and the call instruction on a CISC will actually push the return address. So
yeah, and if you look at concretized call, you will see horrible stuff.
Well,
because PowerPC
hang on, rather than the value judgment,
third thing.
Hang on. The important thing is, with the difference between a link register and a pushing of an explicit return address, the JIT needs to use the link register in calls. It mustn't turn every call into something that looks like a CISC call. That would be very slow. So in a leaf call, the return address is in a link register on the JIT, and the link register would be pushed during frame build, whereas with a CISC, the return address has already been pushed; it's implicit. But on the other side of the VM, in the interpreter, the co-interpreter as it's called because it works next to the JIT, the co-interpreter needs return addresses available on the stack, because return addresses are what point to send instructions. So after a send instruction is a call. When we want to patch a send instruction to link a send to make the call instruction call the new native code, we need to find out where that call is, and it's the return address on the stack, which is the return address that follows, that gives you that information. So lots and lots of the machinery to do with manipulating sends is to do with explicitly using return addresses. So to isolate the co-interpreter from the difference between CISCs and RISCs, we arrange that whenever you're in the co-interpreter, a return address is available on the stack. And so when you want to have a look at a send site, the return address is there. You don't have to find some way of accessing the link register. So what that means is, in all of the glue, when there's a transition from machine code into the interpreter, there's two different forms of the glue. A form for when there is a link register, and that would need to be explicitly pushed, and one where there isn't, because the return address has been pushed by the sixth call instruction. So I wouldn't say that it's ugly. I would say that without having traits or multiple inheritance, it's very difficult to arrange that all of the machinery to do with the preparing of the jump to the interpreter goes through a class which would implement the two differences. So what you see in the code is, if the backend has a link register, generate this sequence of code, otherwise generate that sequence of code. And unfortunately, there's like at least 20 occurrences of those, maybe 10. And it's unfortunate, but that kind of architectural difference is really important for extracting performance. It would be very easy to turn the thing into a CISC by always pushing the link register, but you don't want to do that. But I'm still very open to trying to restructure the code to make those kinds of if then else choices more elegant, expressed in a more object-oriented way.
Sorry to jump in. What do you want to do with this, Boris? Do you want to now compile it for ARM, or you have the?
Well, we do have this on ARM. We do have this on ARM.
Working. everything?
Yes, yes.
Okay.
That's what that's what I started, because as Elliot said, and yes, in yesterday's opening talk, and this is a principle that we always followed back at OTI, and I strongly believe in, is that you never get on a project that will last 10 years without producing any visible, tangible results that you know exactly that, yes, maybe not really push it into production, but at least you can see the thing working. So the principle is that you go from a happy state where everything works to a happy state where everything works. So the thing is, this was the first time I was looking at this huge cog beast, and I didn't understand what a co-interpreter was, and how this goes through slang, and there's just if you browse all that VM maker category, it is huge, and it is unless you want to spend just reading that code for 5 years before you can understand it, is really we've got bigger fish to fry. So I wanted to go to start with something that works. That is the actually, if you go to get rid of that cog P down there so that you can see everything, because that's a filter, right? And go to JIT. Right. So there is a cog ARM compiler. Yeah. This is in a state where it is fully working if you actually run a simulated VM on a real target, right? You see, many of them don't have. Oh, wait! You need to go to the playground and say cog ARM compiler recompile for the same reason. Yeah, just change power and ARM. Yeah, cog ARM compiler recompile. Yeah. Did you do it? Yeah, and then that. Yeah, that. Okay, and if you look at the concretizers, yeah, okay, good. You see, many of them, they have these ranges, but some of it, yeah, that's kind of, I usually, you see, concretize invertible and something, right, there, or concretize jump full, right? So they have still the old notation. So what how I learned about how this works is I said, okay, I will start renotating them using this pure assembly without, yeah, you see, yeah, there is BX, yeah, move CW into R, that is, I believe that is notated just with the auto assembler. But some of them are still there. So I was like, okay, well, I can debug through it. I can follow the logic how Elliot did it. And at the same time, I have, half of this beast is my stuff and half of this beast is the original stuff. But at every step in the process, I never had a day where the whole VM was dysfunctional.
For me, it makes sense to statically translate the descriptions you're getting from the theorem prover into code which looks like this, because then the process both of bootstrapping the metacircular VM with the B style and the generation of the slang style VM works. So
but you can very easily do it, and we could do this now at the hackathon if you want. Like Pocho, if you click on one below, concretize jump if CC, right, and hit Control-I. All right, you see the one item in the ordered collection?
Yeah, compute jump target offset +8, which it's got to do, right? Which is, yeah.
So that, yeah, no. Literal 6, expand literal 6.
Oh.
Yes, you see item number 1. That is the assembled form of the instruction. And what you do in slang, this is your shift and BTOR.
Yeah. But
So
I don't want to,
8 bits, which are statically 58. Then the next thing, if you click on self, or if you go to meta, to the meta tab, there is, and go to AST. No, not contexted. AST. It has children or something like that. Get children or.
It was a get for
No. Kind. IK. So there is kind. No, not kind class. Wait, what was it called? No, not sort. Sort is the other one. No, term. Yes. Control G over term. And now, if you go, yeah, look at that. So it is a concat between BV8 and that other expression. And if you go to meta, you will see that it has children or something, args actually. The kind up, yes, up, the first one. And it has args, the first one, the second one, args, and Control G there. And you see, right, and it has functor name, which is just concat. So what you're doing here is you're traversing an AST, this internal term inside the theorem prover, but it's trivial to translate that into C.
Well, I don't want to translate it into C because I already, then I'd have 2 translators into C. I want to translate it into Smalltalk. You can interpret this thing, but you could also compile it to Smalltalk. And if you compile it to Smalltalk, everything works, and then you don't need your interpreter. So the value here is in extracting the AST. Interpreting the AST has no benefit. So I would look to translating from the AST into Smalltalk and to execute the Smalltalk.
No, because you can directly execute this.
I know you can.
The Z3 theorem prover can directly execute this and give you in a symbolic algebraic form what will come out of that. And the beauty of it, that you can take this instruction in its symbolic form and do a store into the end zone, like consider it to be instruction memory, and then if you're not in ULD, which executes over some kind of concrete processor, be it simulated or physical silicon, but you can also exactly that same API, and because it's Smalltalk and everything is polymorphic, what you have is a symbolic implementation of the same alien processor API, and then you can execute these instructions which are themselves symbolic, And this is, I was showing this at the last, not PLDI, but VMIL, is the novel approach that no other symbolic execution engine can do, is that they can symbolically execute concrete instructions. So if you do add immediate to register, I don't know, EAX, so the instruction is add 5. So you have the instruction that is concrete. You have a symbolic state before executing the instruction, which is, I don't know, A is in EAX. Then you execute the instruction, and the symbolic execution engine gets you A+1 as the value of EAX. Well, for a JIT, this is no good, because the JIT itself has generated the instructions that may vary depending on what was the operands on those ASTs. So if instruction itself is add EAX B, then at the output you will have A plus B inside EAX.
It's just I don't see in, for example, the B architecture retaining the AST interpreter at runtime. Can you see that?
I don't understand. This is the AST interpreter. Like your processor, if its implementation, if you instantiated the processor to be a symbolic processor, then you don't need any other AST interpreter.
No, I think the Elliot's question is more like, you know, if the thing is, in B, if we would use that, then because everything is AOT, we can at runtime use Z3 to, you know, actually give us the bit that we have to store it to the binary. But as soon as we cheat, this is probably not the best way. We want to do the, you know, bit manipulation using AND and ORs.
Right.
So what is Elliot asking, if I understand correctly, is just to translate this AST into something that can do the bits. We all know that we can do it. So, you know, it's just a matter of
obviously we obviously can do it. I'm just not seeing the dynamic, like maybe is to statically look at it as a piece of Smalltalk for aesthetic pleasure, yes, but in terms of execution,
that's
this already can execute. And in terms of translating to like slang translating, if we desperately want to go through GCC for whatever reason, we can translate this into Smalltalk or into C if we want. It's not, I mean...
Okay. So
I guess in foreseeable future, Elliot wants to
Boris, the question is, what would you translate it into in the bootstrapped executable form of the B execution engine? So if you implemented this and you implemented it in the context of the DMR, right? What would you want executing at runtime when the DMR jitted a method?
Just this.
So you'd actually want the DMR to be interpreting an AST to generate instructions instead of just using bit manipulation.
Well, but in AOT mode, there is no problem for it.
You could.
But let me ask a question, because I think maybe it's something that Elliot is wondering. So you to be able to generate instructions, then you would need to have the C3 running on the background, right? So
Oh yeah,
you
and
don't really.
if you are AOTing the big kernel, then you have no problem.
Okay, but yeah, in the context of JITing,
I really don't understand that statement. If you're AOTing it, why don't you have a problem?
Because you have all the time of the world, I guess.
But hang on, in the runtime of the AOT that you've AOT'd the whole JIT, right? You still have, as I understand it, in the executable of the DMR, a Smalltalk runtime functioning as a JIT, right? Which is then machine code. And
yeah, I agree, and that's the question that I think to be answered by Boris, which is yes. So when you are bootstrapping, you can afford to use the abstract instructions to generate native code and bootstrap everything. But there, when you run that runtime and you load the JIT compiler there, then maybe you don't want to have well, not maybe, probably you don't want to have this C3 running on the background and taking a lot of time to generate native code. Is that
I mean,
correct?
there are many deployment contexts in which you wouldn't have the ability to
where you cannot link to Z3 because and then I guess this is something that I have not implemented, and simply because I think there are very many possible implementations of this. Like you just translate it into whatever you want, right? One option is if you are really in love with Slang, you can get Slang out of this, or you can have Smalltalk out of this, or you can simply have, I don't know, machine code that will be doing this kind of bit manipulation even.
But you do have machine code doing the bit manipulation when you go through Slang, and you do have machine code when you go through the AOT, when you go through the DMR. In the end, the thing that's doing the manipulation is machine code. But you can't expect Z3 to be present when you're deploying on bare metal. And it doesn't make engineering sense to interpret the AST when you can AOT it. Now, you've already agreed that in producing the production VM, we are going to be compiling these ASTs. And all I'm suggesting is that a better path is to compile to Smalltalk, because we already have Smalltalk to C compilers. We already have a Smalltalk to DMR runtime compiler, and so it doesn't make sense adding these other modalities. It makes more sense to me to
no. We can have this modality and compile it to Smalltalk. The problem is, after we have Smalltalk 25 that will be able to symbolically execute execution paths, then yes. But right now, the value in this is that if you just add bit manipulation, then how are you going to symbolically execute this to prove that this produces the correct result?
Well, that's easy, right? You've already got these symbolic instructions as pragmas in the methods. So you can retain that, right? And then you can have a concretize, which interprets the pragmas rather than invoke the pragmatized methods. So with a very small change, you could have the ability to have both modalities. So the method would look exactly like it does now with the pragma,
Right. Okay, now we are on the same page that we need both modalities.
Right.
Yeah.
Right, and so that's what I want to do. It's that keeps us in the happy state, and means that the existing tool chain completely works, right? And it's a trivial compiler to write, right, from the AST to the inline machine to the inline Smalltalk.
To the inline Smalltalk, yeah, it is. So this is but this is then no different from what I said, that this is trivially slangable.
Yeah, and then it's not an issue, right? But I want to see it now. I would love to have this now, right? Because then we're in the happy state sooner, right? The existing
Right.
right, and we can I could immediately start playing with the proof, right? I'm very anxious to set up the multiply example as a proof and take my 2 mistakes in implementing multiply on ARM v8 through that process and have it prove my mistakes. That would be superb.
Wait. How does this affect anything other than than slanging of the production VM?
Well, in the simulator, in my simulator, it means that I don't have a dependency against Z3, right? And I can see Z3 as a compile time and a test time rather than a simulation time thing. So it suits me. It suits my workflow.
I am not sure if you can avoid having Z3 altogether. Well, simply
no,
because...
you can't. You don't want to avoid Z3, but it would be nice to be able to run the simulator without Z3. It would be nice to have a system where Z3 is used in the definition of the backend, not the execution of the backend. If Z3 is a compiler, not an interpreter. It's kind of the same rationale behind the Open Smalltalk repo, where with Slang in the first place, what people did back in the day was there was no C repository. If you wanted to generate a VM, you had to start up an image, you had to run Slang, you generated the C, you compiled the C, got your VM, and then you basically threw away the C. And the disadvantage was that then you have no versionable artifact, and you have no guarantee when you load the VM maker at a later state that its output will correspond to any previous input. So it makes sense to have a versioned generated artifact and to compile that to produce the VM, to have this 2-stage where you go from the Smalltalk VM, generate the C, and then from the C, which is version, compile. In this, Z3 would be invoked to define or refine a processor specification description and to generate an implementation. But to run the simulator, you wouldn't be dependent on that. You just you have the generated Smalltalk. There you go, and there's nothing to you're not restricting people in that way, but by insisting that Z3 has to be there, and the only way of generating instructions is by interpreting ASTs, you're introducing new dependencies plus performance overhead, it doesn't feel right to me. You know, I love the idea of the automating the generation of the back end, and I hate the idea of attaching the back end to
Yeah. Lugging it with you all the way into production.
I have a question. Up to now, do we have any generated Smalltalk code in the image, or is it all handwritten? Because if we start to have generated Smalltalk code, it would be nice. Sorry, it'd be nice to keep them very separate. That was a big problem I had trying to understand Klein, which is a self-written in self. And the handwritten methods and the generated methods were side by side. And I never knew.
There is nothing. There is no auto-generated code that is any kind of Smalltalk source.
Hang on, Boris.
That's generated.
Boris, excuse me, that's not true. So the thing that makes it easier, Giselle, is that with Pragmas, you can tag the generated code trivially, right? Then it's very, very quick to collect it. So I think in COG, there's at least 2 auto-generated things, but one of the auto-generated things is because I didn't have traits when I started, and I didn't want to rely on traits because there was a big brouhaha between Faro's traits and Andreas's nano traits and stuff. They just didn't want to have the dependency. In implementing the stack interpreter, the co-interpreter, and then the multi-threaded interpreter. The multi-threaded interpreter is a subclass of the co-interpreter. And the way that the Back to the Future VM is written is that it makes sense for each concrete class, which then gets translated into C, to have a simulator class, which does things like, okay, this is the Smalltalk version of adding 2 integers together, where because we've got infinite precision, afterwards we have to AND the result, right, to restrict it, and then there's the C, which is natural. So you've got a COG VM simulator subclass, and that subclass has like GUI in it and stuff. So it's quite, it's large, lots of asserts, lots of testing, lots of metaprogramming facilities for configuring the VM, etc. So I didn't want to have to replicate that huge simulator subclass. So instead, I have the co-interpreter MT, and then the simulator. And at startup, the simulator checks all of the methods in co-interpreter MT against all of the methods in co-interpreter. And it auto-generates a shim method that says, okay, if the variable is set that says I have threads, if the thread manager variable is non-zero, then perform the co-interpreter MT method, otherwise skip. Right, so I've got one copy of the simulator, and then I have this class that I can basically elide because I all of the message sends can go past it, right? And that's auto-generated every time the thing starts up. So it's a horrible hack, but I'm sorry, you're there. The photograph said it is a horrible hack, but yeah, it was very nice to be able to do. I think that there's great value in being able to auto-generate.
Right, and it'd be nice if, for example, we would, when you're looking in the browser, if auto-generated code was read-only by default, so I'd have to select a menu if I really want to edit it, for example, because like I said, that's what made Klein like 10 times harder to understand than it should have been, just because I was editing this method. And then after I was done the 2 hours of work, I'd see, oh no, these guys are all generated automatically. Then here's the guy that actually I have to edit and then regenerate them and stuff like that. So just to avoid that kind of stuff, I think that It's a tiny little patch to the browser if needed. We already have little icons to the left of the method names, right? So you probably can have a generated little icon. So I just looking through, I already see the generated stuff, and then if I try to not paying attention, try to edit it, it says this is auto-generated. Are you sure you want to edit it? That would make it.
I think people in Faro are already using generated as a pragma. There may actually be a problem around, but I think that this is useful. You should kick off, send a message to Squeak, Faro, and Queese proposing it, and maybe somebody will come back and say, yeah, we have this already, and then we can adopt it. But I think it's a great idea.
Yeah. I'd imagine somebody already did it. So.
Yeah, but push it through. Don't let it just be an idea. The browser hack is really useful. Sorry to cut in on you, Boris, like that, but there is auto-generated stuff in there. It's shameful auto-generated stuff, but it's there all the time.
Okay. No, I meant that I don't auto-generate stuff.
Right.
Like when I read a processor specification, for example, I don't transform it into a bunch of Smalltalk source.
Right.
All that it gets transformed is a bunch of live objects that just represent the ISA by their state, not by Smalltalk source.
Right.
Okay, so and now we are already 2 hours and still doing some talking. How do we proceed?
Well, actually, we have. I think. Well, yeah. Okay. We at least we have put this thing into the image, and not only image, but we have seen that it actually functions. Because to be able to just start it up and load and say cog arm compiler recompile, and it generated all of these ASTs for every instruction. It pretty much means that everything, like all the hardest the pieces of the setup, just automatically worked. Frankly, I was expecting it to go into a lot of trouble. So yeah. So here is an idea. Is that remember back in July we were sitting and wrote. What is it? If you close all of these. Shall I say, tools, inspectors and browsers, and you go to the category called, inside there, inside the PowerLang. Remember, we added a bunch of classes in the sub, or TA, there is PowerLang/TA or something like that in the packages. There is PowerLang TA or TA PowerLang or something like that. Where is it? No. With we added ARM assembler or.
Maybe we have to add another package.
Oh, you have no. Oh, sorry, Pocho. I know. Go to Iceberg. I know what's wrong. Go to Iceberg, because it's not in the baseline. That's why. Yeah, double click. You see PowerLang-TA, not loaded. Just load that. All right. Yeah, and there is yes, and there is nativizer, and there is ARM code generator. And when we implemented only one, and that you want to recompile that, go and say ARM code generator recompile. That, and then just double click on the ARM code generator, and yeah, and double click on the code. Yeah. There. Yeah.
There it is.
All right. Yes. So this is where we were. This is where we were back in July, and we stopped implementing the bnativizer on top of this same thing. Now, what my general idea was that it would be a complete waste of engineering resources to have the full nativizer there on the COG side and a full nativizer here on the B side. And I was thinking about that maybe we can think how we can unify these two APIs. Because this here, as far as I understand it, is like the difficulty that the fundamental difficulty that I see here is that this is a one-pass nativizer and COG is essentially two-pass. That first you generate a bunch of these abstract instructions, and then you go left to right over the array that you just generated, and you concretize each one. And here we don't really have something like that. Now, what I find what I found really limiting in the summer when I was trying to debug the COG Power PC compiler was that they are not really objects. They are statically allocated structs that go into a struct array, and then you're just reusing, like at each compilation, you just reuse the existing instances from left to right. And then you're overriding. And for example, when you put them into that map, which instruction in the end zone originated from where, you are really having a hard time because you overwrite those instances of the RTL instructions all over and over and over again, and if you're trying to look at what was the RTL at some point, the data is gone. So maybe we could try, somehow fixing that. That's for a bigger picture, and a smaller project is because we already have this. Maybe we can just hack inside here, because this we were trying that with a Gem 5, but because I checked and it still works on real ARM chips, I can drive you through that. Like, you will be driving, I will be just telling you when to turn into which street to actually debug this nativizer on the real Pi, so that we can end up with something like I don't know, 5 factorial, or what was it, or get halfway to the nativizing 5 factorial and see it actually run on the Pi.
Well, if you can I will use my hands to make what you say. So
Well,
it's just
first
right.
I want to hear from others. Are they interested in following this agenda? Because if it's just me and you having fun and everybody else sleeping, and then saying, "Oh, it was a bunch of geeky shit," you know, I don't want to. I don't want that either.
No, I think it's
Well,
good.
speaking of that, for quite some time we didn't hear from anyone else. So I wonder.
It's fine. It's all geeky shit, so it's fine.
Elliot, what do you think? Are you interested in this agenda, or you want to do something else?
Well, I'm happy to you know on the issue of merging cog and B. There's some architectural understanding that we need. So the rationale for having these instructions is just in the runtime they're stack allocated, and so they don't persist. So having things that do persist from run to run, so that you can map back from the generated code at any time, is perfectly possible, because in the simulator we can create the instructions anew, right? The reason why they're not created anew is so that they mimic the stack allocation that happens in the real VM.
Yeah, I understand that. Yes. Right. And I can show you here, like I can tell Pocho where to click to show you that code that you asked me to explain yesterday.
Yeah.
And obviously, I mean, it does work. It's just that fundamentally, the cog JIT is a two-pass compiler.
Three-pass.
And what's that?
Three-pass. So the first pass, we make a pass over the byte-coded method, and there's an array parallel to every byte in the byte-coded method, every instruction byte in the byte-coded method, which is the fix-up arrays. And the rationale for that is that it identifies, amongst other things, the location of backward branches. So if you have a look at the HPS instruction set, every backward branch must be to a loop head bytecode, which is a special no-op. And it exists so that in the JIT,
yes. Okay, I get it. Yes. Now I see what you mean by
when you hit a loop head, you know that this is a join point, right? And so you have to flush all you flush all cached state in registers, because there will be a backward branch, and so you discard everything and you have only what's available on the stack. So I didn't want a loop head bytecode. And the pre-pass over bytecodes, which spots, for example, backward branches, also does other things. It tells us, do we create a block? Is this a frameless method? One of the things that we do in the JIT is have one. If we detect that a method is only assignments and no sends, so it's a typical, instance initializer, then we create a split where we have one test of the receiver being in new space, and then the assignments proceed without a store check. And if the test fails, then there is a store check. And so that first pass allows you to do some nice optimizations and eliminates the need for a loop head bytecode to come back. So then the second pass is the generation of abstract instructions from the bytecode, and the key structure there is an elaboration of Peter Deutsch's stack simulation. And I'm very curious to know what the BVM does. But the idea in the stack simulation is that every time the JIT encounters a bytecode that produces an operand, a descriptor for that operand is pushed on the stack. So the stack is a simulation of the context, and it gets initialized with a descriptor for the receiver in the 0th position, and then descriptors for the arguments and the temporaries following it, and then there's empty after that. So every time you execute the JIT encounters a bytecode which produces an operand. So say you're doing like a temporary variable a plus 1. So you encounter the bytecode that says push temporary a, and so you index the stack to find out where temporary a is and push a copy of its descriptor on, and that descriptor would say, I'm this reference, I'm this distance away from the frame pointer, and I'm a memory read. And then when it consumes the plus, the 1 bytecode, it pushes a descriptor which looks like I am the constant 1. And then when it executes the plus bytecode, that's when it actually consumes the operands off the stack. And now, because it knows that 1 is a constant, it only needs to generate 1 tag test on the temporary variable. So that structure is central in doing register allocation at point of send. So in the COG-generated code, the receiver and up to 2 arguments are passed in registers, because when the send is generated, we haven't pushed code onto the stack. So in a naive JIT, when you see a bytecode, you generate an instruction for it, or you generate the instructions for it. And so all that means that you can do when you see a constant is push it onto the stack, which is the last thing that you want to do. So indeed, this simulation allows the JIT to generate reasonable code for jumping without reifying booleans into the true and false objects, maintaining the flags, etc. But all it allows you to do really is optimize locally. So it allows you to optimize the addition and subtraction and the calling convention so that the receiver and 2 arguments are in registers. But we want to go further so that we can use that stack structure so that, for example, a temporary on the stack can be tagged as being in a register. So then when we actually come to generate the reference to A, we would find out that it's already been in a register. And the problem for that is, okay, the processor has some number of registers. The code generator has descriptors on the stack, say A plus B plus C, right? And it grabs the descriptor for C, and it sees whether it has a spare register, and if it has a spare register, can assign C to the register and generate a memory read that will read from the stack into that register, and then from then on will not need to read the stack, can read from the register. So if you did A plus B plus C, there would be like an inline path where A and B and C were in distinct registers. So if you think of an if then else, you have the traditional code flow problem where in the if true, 1 set of assignments to registers will be made depending on whatever happens in the if true, and then in the if false, a potentially completely different set of register assignments would be made. And so what we need to do at the join point is generate the permutation, the minimum change permutation, so that the else block as it falls through has the same register assignments and the same values as registers as the if true. Actually, it's the intersection of the two, and so you'd have to reload. And then exactly the same problem happens for a backward branch at a loop. So that stack simulation is central right now to reasonable code quality in COG, and is central to doing good register allocation in Sister. So then finally, the third pass, you have the abstract instructions that you've generated after you've used this intermediate data structure of the stack simulation. And you have all of those instructions. What deferring code generation to that point allows you to do is branch spanning. So again, there's like a two-pass thing in that final pass where we go through all of the instructions and we compute their maximum size. And then once we have all of the maximum sizes, we can compute branch spans, knowing that branch spans are no more than what they are with the maximum sizes, and then generate short branches on processors that support short branches, of which there are many. So ARM v8 has a form of short branches. Certainly all of the x86, x86, 64 have different size branches. So we can generate short branches where the span with the maximum size is short. And then we have to arrange that when we actually generate code with the actual size, we don't generate a small branch would it have been large with the maximum sizes, because then you can get an oscillation and you never get to a fixed point. So the size of a branch is tagged when you do the span computation against the maximum sizes. And then finally you generate the code. And then if you like, there's a fifth pass where the sized code is then concatenated and spat out into a region of memory where it forms the method. So to be accurate, it's a three pass where there's an analysis pass of the byte-coded method. There's a compilation pass where you do some semantic analysis of the bytecode by basically reconstructing a kind of an AST in the stack simulation, and then a third pass, which is itself composed of like three passes, if you like, of mapping from abstract instructions to concrete machine code, sizing the jumps, and then concatenating. So Pocho, what happens in B? I don't want to lose anything, right? And I don't see any difficulty in keeping the stack simulation and the instruction processing, the kind of three pass, and expressing that within the DMR. But if the DMR has something better than the COG code generator, then okay, it makes sense to throw away COG.
Well, that was a lot to absorb, so I am not really sure how to answer to that question. But
well, okay, let's take it step by step. So in the DMR, what's the first thing you do with a byte-coded method? Do you simply immediately start looking at its bytecodes and generating code directly, or do you build some intermediate data structures, or what?
So let's go to the code. What you get when you are nativizing is the method sExpressions, right? Which is this low-level ASC. And there you will just emit assembly directly in one pass. Yeah. So let me go there to the nativizer.
And so in B methods, do you have bytecodes or you have sExpressions?
We have AST codes.
AST
which
codes.
are currently they are nested arrays of integers.
Right.
In a more efficient future, then it would be just a byte array.
So
encoding.
Okay, so that's cool. So could we agree? This is a proposal that the DMR architecture and the architecture of the bootstrap and the architecture of the meta VM is of what's what's valuable, and that in COG what's valuable is the semantic analysis, the stack evaluation, and the abstract instructions, and that if we merge those, what we're doing is completely eliminating slang, and we're adding the DMR bootstrap to COG.
Then I guess that there are many views of that, and so the answer would be a little bit more complex. So because I'm not really sure how that would be in the end, what shape would that have. For example, what I have in my mind is that there are like different tiers of Smalltalk. So you could have, for example, a low-level tier where you execute your virtual machine, where you have maybe less availability for creating objects or things like that. And the higher tier, which will be something like a Squeak, where you can do more complex stuff. And so it doesn't have to be the same metacircular runtime running both things. You can have them split so that if you want to have, for example, more complex block evaluation in the higher tier, you can do that, and you could still have a lower tier where the block evaluation is it's different for different reasons, for performance or whatever you want. So I'm saying this because I'm not sure how to merge things, right? So that could be one possibility. Maybe,
Okay.
I don't know.
It's clear how to merge things. I mean, so jump in when I say something that's completely wrong. So my understanding is that in the DMR, by taking a closed world assumption over the kernel Smalltalk and the DMR JIT, we can bootstrap to produce native methods which use something like the VSE binding semantics, where each method is preceded by the classes for which it's valid, and every send within the native method is a concrete call to another native method. And so we have
we have some kind of closure of methods that are going to be executed or something like that.
Yeah. So that can be applied to any closed world of Smalltalk.
Yes.
So you can take that and apply that to the CogJIT as it is, and now
Totally.
you have a CogJIT which doesn't use slang, and which is fully bootstrapped. And
Yes.
the thing that you need to do to fully bootstrap cog, so that the uh, the JIT that is produced by cog, is to generalize the binding semantics, so that we don't have to generate picks. So that as an alternative, we can do either something like Giselle proposed, or we can do something that's like in the current DMR, where we have the VSE layout. And so the work that needs to be done is to refactor cog so that it can have a different, so that the binding semantics are plugged in. It needs all of the binding semantics pulled out into a class, which is a class for an open world Smalltalk and a class for a closed world JIT. And that class, then one of them will have stubs for relinking, because there will be no relinking, right? And the other does do relinking, etc. And that would be a very, very nice improvement to the architecture, to factor out binding, and then that would enable, for example, Giselle to do the ring methods as an example, right? You could just plug it in to the existing structure.
Yes, what you are saying is totally doable. It's actually what I had in mind. I wouldn't start by making the closed world assumption. I would just start with something that lets you create objects freely, um, that lets you send messages as if they are uh, generic messages. They will be evaluated, they will be sent. You will get a send site for that, an object for that caches the send. You can pre-allocate or allocate more send sites if you need. And then in a later stage of optimization, you say, okay, how many? Well, not even how many, but can we change this to a closed world assumption? What does it require? We have to generate a closure of methods, and then remove the send sites and replace them by calls. But the easier way is to just use it as it is right now. Is you send a message, so you get some send site generated for that send, and you call into the lookup. So the cog JIT will just be a Smalltalk code.
Right. Excellent. So this is the far ambitious side of where we want to go. Now, obviously, it is not manageable in one piece. So how about we start with something really, really humble, because, well, unifying the actual two JITs is obviously not for a whole day even, or not even for a 1 week, but we can do something much smaller, and we can like to familiarize each other, with the, like, you cannot really unify two things unless you understand both, more or less. So as an exercise in understanding B, maybe we can continue and run this, I don't know, run some nativization code and inject it into an actual hardware target, and that way we will see how B works. We will see how the ULD debugger debugs stuff and injects stuff into a running target, and we will borrow code from the cog port of the JIT. So like basically we are seeing all three sides of things. Any comments?
Yeah, that's a good idea.
For me.
What example method are you thinking about? 20
We had back in July, we were sitting together and we wrote this in the PowerLang TI, the beginnings of, but I don't recall what exactly what exactly we fed to the nativizer. It was one S expression, right?
Yeah, maybe it was something like return a value or something like that. I am not sure.
We did a. Let me look at the. You know what? Let me look at the actual. Let's look at if you look at the branch, right? There are two commits. No, I'm not looking at the right thing. No, that's where is my okay, GitHub, and here is PowerLang, and in PowerLang branch VM Hackathon, the last two commits. So we started writing a we did a test, right? And in that
we have 3 tests.
This expression nativizer, false literal, method literal from ARM code generator. And I don't believe that will work now because there was some conflicts that I just simply, oh yeah, AST code test in PowerLang tests failing. That creates a remote RAM that and it creates a GDB. If you look at connect GDB, we were connecting to Gem5. What I would like to do is I would like to, oh yes, nativize return 42. Yes. And it has ARM, and the compiler has enough ARM support for it, because the only concretization point that we implemented was load constant into register. Right. How about we start by repeating that experiment on hardware?
Fine for me.
Okay. You have the ARM machine up?
Yes, it's here. I am not sure whether it will work because I am in the VM, so I'm not sure I will be able to reach it. So, let's see.
Well, if worst comes to very worst, we can switch to my screen and then I will drive, because mine I checked that it does work.
Well, it's there.
Okay.
I can even SSH if you want.
SSH into it, please do.
There we are.
Now go to thin shell that you compiled yesterday or 2 days ago.
And here, what should I do?
Go into Squeak, and then go into ARM. Okay. You see, you have an elf. Now, GDB server. One word. Yeah. No. The name of the machine, whatever, Raspberry Pi. Or that, yeah. What was it? 68?
Maybe I have to specify the port or something like that.
No. Wait, it is not 7. It is.
You mean the host?
Yes, this machine. 65,
well, this
right?
What I don't really know what you mean by this machine. So you mean this machine? The Pi. Okay, that was the IP of the Pi.
65.
Oh, sorry. Yeah, 65. You meant?
Yeah, 65.
Okay.
You just SSH.
64.
64. Colon 7000. Yes. Then space.
Oh, space.
And ./squeak.elf. Aha, perfect. Okay, go to the Faro thing. That. And look for. Wait a sec.
I'm not sure this will work. Maybe. No, I think we will need more for this to work. Let me look how to create an initialization environment for testing that is not broken.
Wait. I want to start with the simple things.
Okay. What do you want to do?
I want to just make sure that we can control the Pi from the image, and there are tests for that.
Okay.
GDB category, there is. Wait a sec. Yes, the class is named ARM32 GDB test. There it is. Right. Do not run it yet. Go to host IP and put that, that's 64, whatever. Yeah. Right. That's enough. And then, well, yeah, that's not interesting. Okay, go to the console of the Pi again.
Well, I don't know why this always opens a new one.
All right. SSH into the Pi. The problem is you cannot you cannot control C out of GDB server because that's gonna send the controls to the inferior. Right. Not from this, from host.
Why? I'm not sure why it's not allowing another connection. Maybe it's only allowing one connection.
I don't think used.
Sorry. This is the problem.
Yeah, and just kill all GDB server. All right. and then restart the GDB server on the other one. And instead of just running test connect, debug it.
Okay.
All right, and just step over things. I want to see interesting things, whether they.
Where do you want me to stop?
Just over, and then create RAM is fine, and then let's look at what initial PC will be. I just want to see that it correctly reads the registers. Right, go to integer. CA2000. Yeah, that's exactly what the start address in the thin shell is. Yes. Okay, let's look at the first instruction. Right, and then look at both of them. The first assembly is breakpoint 00. Yes, it's a breakpoint. Yep, and the first instruction itself gets automatically disassembled in the print line. Okay, perfect. We have ULD working. Yeah, that's you know what? This should we should add so that we don't have to kill manually. We should go add something to this. GDB kill.
Where?
In the test connect. No, the last thing in test connect, it should kill the GDB. Yeah, that's better. Yeah.
So let's do this.
Start, and then when you simply run it, it will.
Oops.
Yeah, that's fine. Yeah, child exited. Yes. That's exactly what you want. Yes.
Okay. You have a HUD here.
It should instead of just saying kill, it should say that block should write that I am expecting that exception.
Okay. What's the name of exception?
GDB child exited. Yeah, that guy. Yes. Okay, perfect.
So let's go back, and I guess that it was killed. So we have to
just verify that it got. Yeah, it did get killed. Yeah.
And now it passes. Okay.
And verify that it killed the guy.
Yep.
Yep. Killing all inferiors. Perfect.
Okay. So we can close it.
Right. So there was nativized. Yes. So nativization environment was there. And how did we tell it to go to the ARM nativizer? I am forgetting this.
I cannot remember that.
Well, maybe we can just step into it and see what our.
Yeah, the problem is that I have changed that part, so this one is not really going to work for testing. I think it's not going to work, even this. Because the nativization environment doesn't have it spec anymore. So I should do some updating here. So let me think how to do this. We have here the kernel builder. So let me think how to do this. Nativize for DMR. because the nativizer needs some objects like lookup and things like that. Before we could just use it freely, but it wasn't really working. Now we have to initialize it with real objects. So we are going to, let's say, do this. Let's do this. We have this, and we also need the other part.
I'll grab some tea and be back.
Okay.
Oh, that's
So
too difficult. Got to do the same.
Okay. So let's say we do this and halt, and let's check what we got. This is doing it's taking so much, so long. This is really, really strange. This is the weirdest thing I saw. Where this code come from? I mean, this is like I think we have some versioning problem or something like that, so we could expect more problems. Okay, let's just comment all this. There we go. Okay, I think there we are. So this is the thing that we need to use. So the assembler here is going to be the ARM assembler, whatever we put it there. I don't know if Boris is there. I'm going to leave for 1 minute and come back. Just 1 minute. So do we have Boris back?
Not yet. I don't think so. I love asserts.
Did you find one that failed?
It's just, you know, my code is peppered with asserts, and it's like it's not just for checking, it's not just for tests, right? It's also for expressing understanding. My understanding of the situation is this has to be true. Right.
Yeah. So I guess we should do something like this here. Well, we'll see when Boris comes back, but something like this.
Yeah.
Should work.
Okay, I am back.
We finished, Boris.
Everything works. All tests pass.
Your work is done here. Now, I found some strange stuff there. There was some kind of versioning problem. So I took the nativization environment, which is the one that is able to nativize anything here, like methods, complete methods, and I chop off some sections so that it's not really working actually, but it generates a method nativizer with an assembler, and that assembler is going to be this ARM code generator. And let me check the tests. So
yeah, I am trying to remember how did we, because remember we factored out the classical Beat nativizer into code generator, nativizer, and what was that third thing?
I cannot remember. I think it was like, yeah, some intermediate native code generator or assembler. Or...
Well, because there are three things, right, in the nativizer. One is assembler, the other one is instruction selector, and then the third one is the one that goes, oh, there is object representation, right? And then there is the one that goes from like that generates the RTLs themselves. Yeah. And it should be all that code that should be in like if you actually is ARM code generator referenced from anywhere now?
Sorry?
Like if you look at references to ARM code generator, are there any references where we created it?
Yeah, in the test. Now I made this new nativizer.
Mm-hmm.
This creates the nativizer, and I changed the nativization environment or the S expression nativizer to refer to this ARM code generator. So here we have this nativizer. I'm not sure if it's the same. Well, here we have the S expression nativizer.
Yeah, the initializer of yes. That's what we did. So yeah, super initializer and then assembler is the ARM code generator.
Yeah.
And what's in that nativizer? I don't know. Okay. Huh. Okay. And well, I guess that just gives the assembler in there, right?
Yeah.
So if we are now sitting at a breakpoint, then the X expression thing, are we somewhere? There's a hole somewhere, right?
Where?
Are we sitting inside this test in some debugger?
No, we aren't.
Okay.
Well, we have this, but I'm going to close them. They are old.
Okay. Well, can we try? Like,
yeah, of
can
course.
we try debugging this and see what the new nativizer will have as the
So here we have a halt.
So inside, wait. What's inside nativizer?
Okay, here we have a nativization environment. The nativization environment has a cache S expression nativizer.
Yes, the S expression nativizer inside. Oh,
inside it has
its assembler is just a nativizer. No, the code generator is an ARM code generator. There.
Yeah, I don't know why this got like that.
Well, that's how it was.
No, it should have been directly the ARM code generator.
Yeah, okay.
Good. Well, we have a comment here.
Our code for now. Yes, Pocho, I know. Yes. That is the refactoring we did in July.
Okay.
Because the nativizer and the code generator are two different things. That yes, that's what we did in July. The code generator decides how to nativize, like the nativizer goes from something in an S expression to an operation like put an integer constant into register self.
Yeah, if I remember correctly, we have we made a division between what emits the actual instructions and what is the abstract instruction itself. So, for example, you can say load M register with this small integer, and then you call the assembler, which could be an Intel assembler or an ARM assembler.
Yes, exactly.
Because right now, as DMR master is, this the nativizer directly points to the assembler. The S expression nativizer directly points to the assembler. So here we added this nativizer in the middle.
Yeah.
Okay.
Right. So, but now in this image, after yes, load R with small integer. Yes, and then we said ADI regar OMF tag is yes. Yes, the object memory format tag si should be, right? Because right now this is again hard coded, and this should be really factored out. But let's just keep it like that. Okay. And then I remember that it was actually working. And how, so the CG.
Is it code generator, I guess?
Yes, it's ARM code generator. How does it, we wrote code to put it onto some kind of, what was the instruction stream?
It's a byte array.
It's a byte array. Okay, look at spit. Code stream, next put all. So I would like, can you put a breakpoint in there and yeah, and see whether it ever gets hit by that test? Oh, it's there. Yeah, it does. It does. Perfect. Perfect. Spit, and it's on. Yes. Click on spit. I want to see where. How does it get that byte array? Code stream. Where does it get the code stream? Yeah, well, the instruction is correct, I'm sure. So it's a write stream on something. New and oh, I see. It gets it to a byte array, and then what does it do with the byte array?
Oh, here you initialize. There you have this.
That's it. Okay.
And there you have code.
Ah, okay. And how is that used?
It's not used in the first test. In this test, it's not used.
Ah, I see. Okay, so we already have all of that working. What we want is the next part where we install that into the running target.
Mm-hmm.
So I thought, so you've got more than just a PE32 exporter. You as a COF now.
Well, actually not. This is injecting the thing into the memory. Boris will explain it better.
Cool.
Yeah, this is the thin shell, and we have exactly the same thing. How I debug the cog, the PowerPC cog. There's a thin shell which is just an empty elf, and under debugger I just load this empty elf. But what is interesting about it is that it is completely controlled in the linker script which segments have what addresses. So, like, for example, the cogs thing that you cannot write to the end zone as a load from native code, that's all respected. And the idea is that the memory layout, like, remember in that classical 20 years paper, there are two pictures with two different address space layouts, under simulation versus under versus So the idea is that because we completely control what the linker does from the linker script, and because we have a real processor that we can, it's an actual GDB thing, that distinction between the two between the two address space layout is completely unnecessary. And when you simulate, what happens is that you bring up on the real processor or on Gem 5, which is a faithful simulation, but from the point of view of the simulator running in the host image, it cannot tell any difference because to it just looks like a GDB server.
Yeah.
And then when you emit code, you have the object memory, or the memory of the process, which in the classical cog alien based thing you have run in, and then it's a byte array. Well, the byte array it actually shares memory either through the socket that connects you to the RSP server, or if it's a simulation, then it's an actual shared segment of RAM on the host machine. But that's implementation detail, right? You have a port into looking at the inferior debuggee's memory.
Right.
And you're just simply installing, when you read the image, you install it into that running target. And then when you are simulating the JIT under the debugger, you are actually putting those instructions into the memory of the running target, not into some kind of byte array.
Does the thin shell have any output facilities where you can save the binary a binary from it once you populated it, or is not, that doesn't make any sense?
You could have. It doesn't do it now because I haven't found any kind of use for it still. But there is a couple of things you can do. If you are running in Gem 5, you can do a snapshot of a running simulated machine, and that will save everything there. Or you could just take that kind of snapshot inside your outer environment, right?
Well, yeah. The question is, what's the best route to get to a nativized CogJIT for me? And if I take the nativizer.
Yeah, we can think about that. We can think about that. Okay. Oh, Pocho is doing something interesting.
Yeah, I found that the connection failed because the hardware break returned this string which doesn't have a value. And I'm not sure why.
What is it trying to do? So you are trying to
continue.
To continue. No. Wait a sec. Where did you nativize it?
Just before?
No, but it only nativized it into a byte array, right?
I guess that it will write it later here.
Native code, write bytes.
Here is the test that will inject the thing.
Right. Well, first of all, RIP. You don't have any RIP.
Yeah.
Where PC?
Yeah. So the thing is that we were simulating with Gen 5, I think, for Intel, right?
For Intel, yes.
Yeah. We know how to change that, but yet we could reach to this point, and until this point, it should work. So here we nativized the thing. I stepped over here and to let GDB continue, and then it should have passed through some kind of breakpoint, I guess, or maybe not.
It did hit breakpoint, right?
Yeah, it did hit the breakpoint. Yeah,
it hit
but,
the breakpoint.
Yeah, actually it did, and
exactly.
when we are analyzing the answer,
yes,
we get this answer.
Pair 05 hardware break is what is the pair?
So it doesn't have a value.
Answer. Yes, this is the answer. T.
Yeah, T.
Okay. Yeah, we can look at that. We can look at that. We can look at that. That's not that interesting.
Maybe it's an optional argument.
No, I see. I see. This somehow this GDB server put HW break string instead of T.
No, the T is before. It's here.
The T is before. Okay.
Yes. So we got this T. We removed it from the stream.
Good. Yes.
So the code splits in pairs.
Yes.
The problem is that the first pair, which has the 05 hardware break, doesn't have a value.
Doesn't have a value. Yes.
Maybe it should be ignored. Like if the pair, size is this, then
yeah, something like that. V equals blah blah blah.
And if not, I don't know what we want to put it. But just for
just put good at nil or something. Yeah. No, you cannot do that.
Okay.
To analyze continue answer, not C, because if you restart C, it will try to GDB again.
I wasn't going to restart it. I was going to step over.
Yeah, perfect.
Okay, there we are. And okay, so here we don't have
you cannot do that because that's not gonna find it.
Okay, so what are the registers?
That doesn't make sense. That does not make sense. Okay, so it was what? It put it into these are just supported features of this processor, or this GDB rather. You want registers. No, that's processor description you're looking at.
Yeah, but I wanted to know what the registers were, so to imagine where
you're not looking at the right thing. You're looking at the PDL. You want the GDB, not PDL. GDB.
No, I know this is not the GDB, but I imagine that if I saw the registers, I could think which one would be the one for the register. Okay.
No, just no. Look at click on registers.
Where? Here.
No, you're looking at processor description. You should be looking at the remote GDB session, and then
here.
A little bit. No. You see a remote GDB session, that blue thing, and then raw, registers, and meta, the tabs.
Here. Okay.
Yes. Okay. These are the registers.
Okay. Yeah. So it's the PC is here.
Yeah.
And that's what we want.
Shit. It has not moved at all.
So this one is PC.
Sort is unfortunate.
What's that?
The sort of the register names is unfortunate.
Yeah, there could be.
Well, you can click on that where it says register one
Yeah.
down. Yeah, there, and it sorts. Yeah.
Right, and it doesn't do a numeric sort. So.
There
But
is
it's not important.
two views to no. There is two things. There is and unfortunately we cannot see it right now because this is one level down, and we should really do the same thing that it does in Cog, because right now it just manually creates a GDB session. And in Cog, there is one intermediate level of abstraction, which is the alien processor. So what used to be the alien processor in your thing, it keeps exactly the same API. So Cog still thinks it talks to your simulator, but the implementation inside it encapsulates a pointer to this GDB session. And because it is simply an alien, you can look at the registers through your, what is it, processor more for what you call it. A very nice view of
right, the processor inspector.
Yeah, the processor inspector, yes.
Okay, so I restarted the server and recompiled this to use PC and R1.
I don't want. Right. I see. It's down, but not +1, +4.
Yeah.
Why +4?
Well, you see, on Intel, the int3 instruction is 1 byte, but the breakpoint instruction is on ARM is just
here.
the other ARM instruction, which is 4 bytes.
Okay.
Yeah.
And so we'll have to restart.
Mm-hmm. Right, and this is what I was looking for. And this is what I was looking for. The memory write bytes NC code to address where PC. What happened?
Okay. Now it's that we have a compiled method here.
The native code is compiled.
So the native code.
That's not good at all. The nativize should return the code.
Yeah. So, well, we'll save later, but right now we can do this there. Or maybe save it and restart.
At put. What happened?
No, that the test was taking too much time because of the initialization of the nativizer. Okay, there we should be. So the native code right now is a native code. And there it is.
And step. It's not tracks, but.
Okay.
Right. What is the registers? Is it really R1?
What do you think?
That is, yeah.
That is, yeah, for digit.
Yeah. Yep.
And there it is. Well, then I don't know what this is. I think it's something.
This is the epilogue. We were debugging the epilogue.
Yeah.
Can you say that again, Boris? You're debugging
the epilogue of the method.
Epilogue. Sorry. Right.
Yeah.
Okay, so we just executed this in the Raspberry Pi, which.
Fantastic. Fantastic.
Well, it's a long way until you have a compile method, but you just need an assembler, right? You need to start by load 42 into an R register.
Which is what we just did, right?
Yeah. And I have to say also that the all the workflow went quite smoothly, because the other time we had to install a lot of things to make Gem 5 work.
Well, it's just, well, first of all, we had to install libz3, and for some reason it took pains, and compiling Gem 5 took some time, and other setup, and it's much smoother now.
Yeah, I'm starting to think that this script that we made for the hackathon should be somewhere, so that not only the scripts, but also the scripts to generate the VM. So that if we want to generate a VM, we recreate it and start coding from there.
Well, they are already all on GitHub.
They are already in GitHub. Great.
Sure.
Yeah, we should add them to the, put them in the documentation so that the development process is even easier.
Yeah. Well, frankly speaking, another thing that helped a lot is that now we have in Smalltalk we have the baselines, the Metacello baselines.
Yeah.
Because the previous time it was cursing over getting machine arithmetic here and getting the argc here and getting GDB here and all of that stuff. And now the baseline just automatically takes care of all that.
So it was a small step for ourselves, but a big step for a huge step for I don't know what. So we have 15 minutes, 20 minutes. I don't know what you want to do. We could discuss a little bit more. I don't know if you want to cut something else. I also have many ideas of what to do in the hackathon, but I guess that this was needed to get into the system, like a first snapshot view of everything, and we will be able to do more complex stuff or bigger things in the near future. Now that we have this to get into what is what here in this system. I wanted to do. I had a list actually to try things, but I guess I was too ambitious. Like trying to do the experiments with the inline caches, or for example, starting with the some kind of uh, Open Smalltalk VM bytecode interpreter or JIT, or let me recall, I had the list somewhere, or to make experiments with live typing, or for example, to make a graph coloring register allocator for the optimizing compiler. I had lots of different things in my head that we could try, but this was necessary to start with something like this, to get to see what is what, and to explore all the things. We can do that later, all the other stuff.
Well, I mean, there's some really important underlying issues here. The emotional difficulty for me is not giving up control. It's losing the confidence in my development process, because I know that in the current incarnation of the simulator, I can analyze and fix problems. So that's one fear, and then the other fear is the fear of losing parts of cog that I value, like the aggressive optimization, and the fact that that leads forward to the adaptive optimization. Right, this is an architecture that's evolved with a direction, and so I'm if I'm having emotional problems, I wouldn't be surprised if other people are having emotional issues towards ownership, and also don't want to lose things. So you know, emotional realities are behind our attempts to come up with unified architectures, because we have ego, and it's more than just ego. We have familiarity, and there is this justifiable fear of the unknown. So it seems to me that the things that we need to do are exemplified by Boris's beautiful saving of the stack, so that he could correlate the high level to the low level. Is that we really need to get that kind of familiarity with each other's code, and we need we need to have that familiarity, and then to some extent we have to work consciously on these ego and ownership issues, so that we all feel invested in where we're going, and we all have some kind of positive feeling, and that we're not losing. Maybe we won't succeed in that, but I think that we have to address it. So one of the things that's been going around in my mind this whole time, when I asked you that very difficult question, Pocho, was like, I'd love to give you the same kind of tour of the internals, and then at the same time I'm thinking, well, maybe that's completely in ignorance, that what you've done inside the B code generator is equivalent, but I don't think that it is, and so I'm dreaming of like keeping the optimizing architecture of the Cogit, and nativizing it, and going through that project that I said earlier. So I suppose there's me being emotionally honest. I'd be very interested in hearing from you, Boris and Jan, what your emotional feelings are, and what you feel attached to, and what you fear.
Yeah, I think that yeah, I can see what you're saying, and I agree that yes, everybody has some attachment to their code and to their projects. So it's like when you try to make something in a group, it gets difficult to deal with that. What I think is that uh, we can we should do an iterative process on that too, right? It's not that
Yes.
we can fix all the problems in the first day.
Yes.
That's what I try to do. What I try to explain with the different tiers of Smalltalk,
Yeah.
because, for example, B has its own code generator, and code has its own code generator. So which one are you going to use? Well, in fact, you could use both of them, right? So you could use the code generator of B to generate the code of code generator, and then you can use a code generator to generate the code for the Smalltalk bytecodes of the open Smalltalks, right? And that will require quite some work, because, well, you have to think how to convert many pieces of slang that nowadays are translated into C,
Well, it
to
doesn't
make
work.
them.
Okay, so that's one way of thinking about it. But the thing to think about it is that really it's a lot of small talk.
Mhm.
You know, the parts of it that are slang specific. I think constrained. It's
Okay,
very
well
much a,
then that's better. That's better. What I mean is that, okay, there's work to be done there. Probably you are the best that could do this part of the work. And from that point, it would be interesting to see. Okay, so I'm thinking right now. So if we have that working on top of the big kernel, then we are one step closer to being able to share parts of the code generator from one system to the other, right? Um, uh, so that way we can deal with the impedance of having different systems that do the same, but that can work together. Um, and from there we can go on. I think that from the COGS point of view, the most interesting part of B is its kernel, right? For example, for me, there are many interesting things, because we want to make a whole new Smalltalk. So on top of what we put on the kernel, we want to put other interesting stuff, right? But even for you, you could just use the kernel and forget about the rest if you wanted. You don't even need to use it. You can just, for example, continue working on making code, load the squeak on top of the DMR kernel. So that's one way to deal with all this.
I'd like to reinforce something that I mentioned yesterday. So I mentioned that the old project for a virtual memory, Loom, used an interpreter that would switch between two images. And when I started the Silicon Squeak project in 2008, we decided that the operating system would be Squeak in OS. Now, Squeak in OS actually makes DOS look like a high security system in comparison, because it opens up the machine and you can poke in any register, in any IO register you want, in any memory. So I thought, well, why don't we do the Loom thing and have two Smalltalks? One is called the kernel Smalltalk, and it's closed, doesn't even have a GUI or anything, and it runs the user Squeak as if it were running in the simulator, like when Elliot is debugging the simulator, except that instead of really running inside, so it actually would reuse the simulator code for it. So so when the user runs new, so it's trying to create a new object, then the kernel Squeak would use the simulator code to actually it would see the user memory as one big byte array or word array, really. So all the primitives would run inside the kernel image, the kernel VM, and the kernel VM would have the Squeak in OS primitives. The user Squeak would not have that. But so and then why have one Squeak, user Squeak? Have 5 user Squeaks, run each application in its own little image. You compose their windows into a single user interface, but then a crash. So if you play around and you crash one application, you don't hurt the other 4, which are running the individual thing. So it's a tiny little patch, but what this would do is you really don't have to have these would be the tires that you were talking about, very Smalltalk tires would be running. So the actual physical memory is now divided into 6 segments, independent segments, and you can actually have different code. So you could have a different compiler. So you could be using COG for one of the Squeaks. You could be using the code that we've just been seeing in another one. So there'd be this separation. It'd be like a collection of Smalltalks talking to each other. And I was talking about all of them being Squeak, but really they don't have to be Squeak. One could actually be an old Smalltalk 80 that's running some applications. And the reason I wanted to work in that direction was to allow 2 applications. For example, let's talk about Squeak. So we have an application that only runs on Squeak 3. It doesn't run on the modern Squeak. Well, in its own little image, it'd be able to run. But as long as you have some little mechanism for exchanging messages between them, it'd be able to collaborate with objects that live in a Squeak 5.3 image that talk together. So it's so it'd be a collection of Smalltalks that together they allow the user to do a job. And recently there has been a secure operating system called Qubes, QUBES, which runs a Zen Hyper Zen Hyper terminal, and then you run Linux images, or you can even have Windows virtual machines, and it does that for security. So the network stack lives in its own Linux, which doesn't run any other applications. The GUI Windows runs on its own Linux. Sorry?
Yeah, that's the KVM, yeah.
Yeah, so they did that for security. Now, the way that they did it, I don't like it very much, because you need many gigabytes to do almost nothing, because you have many copies of the exact same thing. So, but Smalltalk is small. It's in the name. So applying the exact same thing to Smalltalk, we could probably run in something like 200 megabytes. We could have many different Smalltalks all working together. So I haven't worked on this yet, so that was just an idea. Since I've been going from the transistor level up, I haven't reached that point yet. But it is a way of us not losing our own code, like Elliot was talking about, and yet working together. If we can have these islands of code and exchanging messages and working together. So
Well, I have a lot to say. This emotional struggle is very familiar, and for decades. And the problem is not so much about losing. The problem is more about the size, right? This is a very ambitious the whole is very ambitious, and you're here and you want to be here, and you more or less kind of have an idea where you want to be, and you may start investigating and investing time into learning about this world here, and then you are here, and maybe you may want to instead spend your time on answering the question, well, how do I even launch this rocket off the Earth that I am in? And then in the meantime, what is in between here? You don't even have any kind of idea. And that's scary. And to manage that scary is something that I have met with criticism. I've met with horrible emotional responses from people with whom I tried to collaborate on this project that I have started years ago, from this desire to build this Smalltalk 25, the Smalltalk of the future. I have lost good friends over it.
Wow.
And I think there are two important things. One is the understanding is that the fact that I don't know what is in between, and I don't have answers to all the questions, and to some of these are even approximate answers, is just not the end of the world. Number two is having a sense of security in both ways. One is that security in knowing that, yes, the people who are funding this work, they have an appraisal of how big this project is, and they understand. So, as long as we deliver pieces of it, there isn't really a risk that, okay, well, you guys have not traveled, they have not landed on Mars yet, therefore, this what you're doing is shit. right? So there's that kind of security against that. And number two is the security that against each other, right? That there is very, very many areas of computer science, of mathematics, of a lot of things, and there's no way to know everything. And I have people with emotional reactions that, well, okay, I don't really understand any of this, and I'm gonna appear like some kind of moron, and there's that kind of in purely image insecurity. And I mean, again, I think in this group we are all have enough recognition, and we understand that this is just a non-issue here. So that's about the emotional, like the immediately emotional part of it. Now, the point about, well, there is stuff that we wrote. I really don't place that much value in the stuff, right? Because stuff, in the sense of avoiding inverse vandalism, stuff has negative value. When you write 1,000 lines of code, you have a debt of 1,000 lines. You just inverse vandalize the world by 1,000 lines of code. And I will repeat, for the sake of this whole audience of the hackathon, something that I started saying back in one of the preparatory discussions, and you heard me say that, Elliot, but for the sake of those who didn't, I will repeat this. I will show again these books. This one, I don't know if you can see well. It's I just wanted to, I by complete incident, I got this book because I kind of like having the original printed copies of classical things, and this is just a collection that is famous by like 5 pages inside it, and it's the little paper by Howard, that is the other paper on the Curie-Howard isomorphism. And I just thought, well, this is just, and then when I got the book and I started reading from page 1, and it's a book where every single line is pure diamond. It's priceless and precious, and you wanna spend your life reading this kind of stuff. And there is so much code, my code, and code that I'm touching, that is around it, that is, you start reading or you start writing it, and it's like, okay, what am I doing with my life when there is when there's stuff like this? And I was with a garbage collector and with organization of how objects are represented in the object memory. I was trying to understand why the garbage collector puts bits in the pieces where they are. And exactly 2 years ago, Jan and I was talking face to face with Carl Hewitt, And Carl Hewitt and Jan, correct me if I am like lying about what Carl said, but he was something like, well, if you really want to understand, you need to read my chapters about microplanar, and because it all started from there. And so I got his book. Well, it's not only his book, it's collected papers again. And there are several of them. And the first one is, A Note on Microplanar by Carl Hewitt. And I immediately realized that I just did not understand anything about why the collector is the way it is, and I started reading the book, and I realized that I thought of myself because my first encounter with Prolog was in 1990, and I love Prolog machines. So I thought I was, well, not really an expert, but that I kind of understood something about Prolog implementations. And I immediately got cross-eyed and realized I just don't understand anything about virtual Prolog machines. And I started digging, and then I got this book. And this one is astounding. It's like actual text is like 70 pages. It's a very thin booklet, I would say. And I had exactly the same strong emotional reaction that, okay, well, this is the real gem, the kind that this is when you write something like this, you are adding and not subtracting by inverse vandalism. In these 70 pages, there is from these 70 pages, I got more insight into why VMs, what they're fundamentally doing, more than from the last 20 years of trying all kinds of stuff. So I am not my particular code. I'm not attached to it. I see it as garbage that I simply do not want. Now, about hackathon projects, I also had at least, but I understood right away that there is no way we're gonna fit much into one half day. It's not a day, it's a half day, and not even that, because I thought we would be spending, I don't know, 3 hours on setup, that we spent like 2 hours on setup today. I thought this was for last night, and we were doing it today. So realistically, we had like less than 2 hours of actually doing things. And I had many things. I had I wanted to show to, well, primarily to Giselle, because I'm kind of proud, some some code where you can actually make that you can design hardware in Smalltalk. And I think I'm kind of demonstrating convincingly that Smalltalk is a much better language to write hardware in than VHDL or Verilog. And regarding the Squeak NOS, there are some interesting things, because there is this Australian project with IBM Australia and a small company that are doing this together, that they want to create an affordable, like for hobbyists and students and makers, an affordable make your own open power, make your own CPU engineering kit for learning and fun and whatever. The problem is, even if you want a real computer even with something with RISC-V, you need something like an Unleashed board or something like that. And if you want to really use it for something serious, you also need that extension board. And now we're talking about like $5,000. And if you want to do something with a newly open PowerPC platform,
well, Sci-Fi fixed that problem.
Yes, I know, with the newest, yeah. But open power, if you want to synthesize the A2I or the A2O core, I mean, yeah, sure, they are fully open source and with all the documentation and RTL and everything. But you need an FPGA where the chip itself comes from Xilinx at 25 grand, and there's no ready-made board, so you need to lay out your own PCB, and you have to spend 25 grand on the chip, and you have to solder that BGA on the PCB that you designed yourself, and it's just no, all right, like not even, don't even think about it, right? So there's this project to do a kit to start this for under $99, not quite as cheap as a Raspberry Pi, but still within a hobbyist student budget.
How much memory on
something like the RT Creator or something like that. So
how much memory on that, Boris?
What's that?
How much memory? How much RAM?
Will be on that board? Mm-hmm. You mean like just DRAM?
Yeah.
I think like something like half a gig or something like that.
Because it's interesting, because the Raspberry Pi 4 is around $35 in the, just the bare board in the 4 gigabyte. But the 8 gigabyte version is available, and that's around $85, $90.
Yeah, but that's just a hard, like ASIC ARM. We're talking about FPGA, right? So that you can experiment with your own CPU design. So what I was saying, yes, there is something interesting about that you cannot have a standard, like within that transistor budget, within that gate budget, you cannot fit a traditional development environment with Linux and GCC, and we're talking about things like MicroPython, and for many reasons. And this opens very, very interesting opportunities for Smalltalk, and because if you do Squeak, I can fully realistically see putting something like Squeak NOS on top of that sort of board. I mean, minus the floating point, which is its own disaster. But I heard from you, Elliot, that you fixed that part. Well, in the VM, Prim 7 is a disaster, but I think on top in the image there is a disaster that you start up Morphic and it wants floating point operations, and I don't know whether you can do soft floating point with these things or how you. Well, I don't know whether it's gonna. I don't want to be even dealing with it. Whatever. Yes, and in that sense, it's when I'm working with these people, this is going back full circle to the emotional question, how you deal with the emotional problem. I think the answer to that is what you said about the T people. Is that and what you said about the T people combined with what Gilad said about, well, how do we differentiate ourselves so that that the competition, they are so much bigger. And the answer to that is that even the problem is only attitude. There is very, very big difference. Like the world is the world of computing is much, much, much larger than what it used to be in the 80s and even in the 90s. It's just that distance between the boats. I mean, yes, it is tragic in the Smalltalk community because we're so few of us, but the scale of distance between the different ideas that different people are working on has become huge. Absolute, something that even 10 years ago was completely unthinkable. And I tried it, and I find that it's not that, it's scary the first couple of times. And then I became, what is the word? Addicted. I became addicted to coming to work together with other communities and play their game, learn about their stuff, help them, and how welcoming they are is something that gives you a positive reinforcement then that now you cannot live without. I was scared when I understood that I cannot just simply download and use Gem 5 for investigating the VM, that I have to fix their bugs and I have to contribute the fixes back. And I have to write parts of the simulator that because the central people on the project, they're all work either at ARM or at AMD or at NVIDIA or at Google. They are hardware people, and for the sort of application for debugging a JIT, yes, it exists on paper, it exists architecturally, it's there, but it just doesn't work. There are just bugs. They say, well, yeah, this is how it is, but because of their main application, what they are using this for, they never actually cared to actually fix it to a point where it actually does not crash, and it still crashes in many ways. And then after a few months of doing it, I suddenly got to present at ARM Summit, which is a SIG-Arch ACM conference, and I was like in an invited status because they thought, okay, well, this is really, really unique because this is an application of this, which is completely untraditional and a completely different direction. Then I was criticized that well, this is stupid, to even try because none of us are really experts. That's not true. I mean, you spend a little bit of time looking at stuff, and they invite you to present for an invited talk, and then they make you a co-maintainer of the project, and when you are stuck and ask for help, they literally drop everything else and to help a newcomer. And then there was with this open power micro implementation, this microwatt PowerPC core. So I was trying to port it onto the FPGA that I had available to me, and I mean I know about VHDL enough to just, you know, if something is working, I can with struggle port it to another chip. But when there are really you know, bugs deep in the code, like I don't even pretend to understand that much about hardware. So I was bothering these Australian guys, and I'm in Canada, and the time difference was a bitch, but they were staying up all night, and then, you know, they dropped everything just to you know, to help another newcomer to start being comfortable and start actually fixing stuff, and now I have you know, I was for the hackathon, I was presenting in pure simulation, so that anybody who wants can without going into expense of getting FPGAs and learning how to, you know, very trivially can reproduce my results and start working with that code base. But, you know, I also have it working on this prototype of the $99 board that you know, to make sure that we have an actual performance Smalltalk on it. And, you know, if we find enough points of contact with Squeak on OS people, maybe we could somehow pull it to be a reality, you know, that you buy this board, and then the people will download an SD flash image and just run Squeak on OS on that thing. So yeah, the T people, the T aspect of people, it's not only important, but it's I don't think it's difficult. It's a very it's a pretty straightforward and not very painful answer to the emotional struggle. Jan's turn around the room.
About emotions, we have internal differences. For example, in the old days, we had 2 annual fights on the Squeak mailing list. One was about the Squeak license that had been declared to not be open source, and then people would fight over that once a year. And the other was about having native windows, whether versus doing everything yourself and then just pushing the bits to the frame buffer. So this is an internal.
You do realize whom you are talking to, right?
No, I don't get the context. Sorry.
Well, because back in 1997 98, I did Squeak with native widgets, and then that later became SWT, the foundation of Eclipse, and that's why IBM immediately hired me, and so it's a kind of very personal topic for me.
Yeah, in my case, I had come from Self that did everything by calling X window, and it was depending on what terminal. So you had 2 terminals side by side running Self, and it looked different on them. So I was not too fond of that, but I could understand the people. So that's the internal conflict, and the other conflict we have is the general computing environment. I mean, that's why we had the fight over using the left arrow, which looks like underscore on other people's system versus colon equals for our assignment, because Xerox and DEC decided to adopt ASCII before it was ready, and then they changed the characters and became incompatible with the rest of the world. And the people in general don't like our image. Oh, you're a world unto yourself. No, you should just be a lightweight system talking to Unix or whatever. We had a very interesting Smalltalk from Argentina that was based on that idea. They took a head of a time compiler that Bryce wrote called Exupery. So Exupery was not a JIT; it was a head of time compiler. You'd give it one Smalltalk message, and it'd give you a byte array of x86 instructions. And there was a Smalltalk that took the Squeak sources, but it was a completely new Smalltalk. It compiled ahead of time, and it used native libraries where as possible. So it used as little in Smalltalk as possible. Smalltalk was a tiny glue for native libraries. I don't remember the name. It was the name of a deer from Argentina, Heumu, or I don't remember the name of that. So there are these different directions. So and that involves motion.
Giselle, the name for that was Wemul Smalltalk.
Wemul.
Yeah.
That's great. I don't know what happened with it, but
how do you spell that one?
H-U-E. I don't remember the rest. Did you type it on the chat?
Yeah, I typed it in the chat. It's also a name of an animal. You can Google.
Yeah, so it's this name here. So that was the idea that you could compile ahead of time. So it's not completely different than the B system that we saw, but the idea was to not replicate what the rest of the world was doing, to play nicely with the rest of the world, which is a valid direction to go in. But it does cause a lot of conflicts. I mean, just compare using JIT versus using the Monticello, and I mean, people get upset over it and stuff. So it's something that we have to overcome to collaborate.
Yeah.
Well, a lot has been said, but you know, from my point of view, I am really happy that you just opened that discussion about emotional attachment, because now for me it's difficult to start talking about it, because now I'm going probably to be negative, and maybe too negative, and whoever worked with me for some time know that I'm always the one who spoils the party.
Well, we're already used to it, so it doesn't, it doesn't spoil the party. That's just the way you are.
Yeah, but I'm really happy that you started and that you admit that you, and I am no different from you, and probably no one, they have the personal attachment of things. And I have a feeling that for some reason in Smalltalk community, this personal attachment to whatever project we are working on is just much stronger than anywhere else. Maybe it's just because I'm most familiar with the Smalltalk community, but I think this is the biggest problem of the community, because this prevents us from collaborating, right? That's how I feel. So the first thing is to just admit that that's our problem.
Mm-hmm.
And in terms of how to continue, well, there is a one level which you've been discussing with Pocho to great and Boris to great lengths, like how to use B, and whether we should take a the stack simulation approach for optimizing stuff, which is not used only in Coq actually, but how to move that somewhere else. I think that's a second step. The first step is to share and show what we are doing, and at least be supportive if someone else wants to take it, or if someone else wants to do something else. I don't know how to express that, but maybe I can give you some examples. Right, when we were playing with the Powerlang and B stuff, I was like, and now I'm exaggerating just to make the point, right? So it wasn't quite as extreme as I'm now going to make it. But I essentially said, well, Pocho, this Naturalizer, that just generates a code that I don't like. This is just not a good thing. What I want to do is to use recently I'm working on this OMR Testarossa compiler, and I wanted to use it and try to build a Smalltalk, and then try to use it on a RISC-V port, which I did before. In order to do that, we had to find a way how I can use the B code base and the design of the classes such that Pocho can use his and I can use mine, and still have a quite a large common base. And that means that Pocho had to make a step back and do something for me, because I just wanted to do things differently, which probably makes his life harder. And also, I didn't just go and change it too far, so it suits me just perfectly, because it would make Pocho's life impossible. That sort of attitude. Like, yes, me and Pocho, we were biting our lips, but we still made the move, and Pocho did the move in another occasions too, right? So I think this is the first step, and if we get this working, then the next step is to actually work on the code. That's like, if I go back to the GDB stuff, right? Given my background and my founding, I cannot probably now just jump and do the GDB support for Coq if anyone's interested. But I mean, if you say you want that, I probably won't jump right now and just drop everything and start working on it. If you say I want to help with that, then I'm more than happy to help you, right? And this is something I think we should start exploiting this and work on this, and then we will get a deeper understanding of each other problems and standpoints, and then it would be much easier to make the second step, which is to actually even share pieces of the code base.
Yeah.
But we need to be aware of our personal attachment and work with that, every single one of us, or at least me, to actually be conscious of the fact and say, okay, well, now I think this, but maybe just make a compromise. Not sure whether that's an answer for your question, but
perfect answer.
This just came to my mind.
One of the things it provokes for me is building a project map, which is a very vague thing right now, but is kind of about identifying big architectural components and how they can interrelate, and moving towards each of us has our particular version of the vision, but trying to express that. But you know, that diagram would actually be decorated with the emotional issues in a way, because I think it's really important. I mean, certainly for me, at my stage in my life, the emotional issues are very important, and if I don't address them up front, that, you know, they block me. So I imagine doing that, and I think that would be constructive. I love what you say about asking help. I think that's the right way. Is that, you know, we the commitment that we make now more than anything else should be one to stay in communication, and to keep on relating and help each other and move, and it's not to try and smash everything together at this point, because things will fail. And so what Boris said about making progress is really important. So I think I think I'm glad I asked the question. I'm glad I got the answers that I got. I don't think I could expect much more. I don't expect much more at this point. I haven't thought enough about it. So yeah, I'm pleased. It feels better. I do dream of unified code bases, and I dream of these new tools. But I want my cake and I want to eat it too. So I don't want any of this to make my life more difficult or get in the way of the beautifully fluid simulator experience. You know, it's very interesting. Lots of people say, you know, when Elliot's debugging the simulator, that's not what I do. I do use the simulator to debug, but no, the simulator is my development environment. That's where like 99% of the code gets written, and that's where 100% of the fun is generated. I don't I don't have a neat way of terminating this. That's the way I think right now. I do hope that you know, the illustration that Boris gave of how to use Smalltalk to make things comprehensible is something that we put effort and imagination into, and to try and understand where we all are and how things can together. So this is a challenging project, rewarding and challenging. It's nice it's important to approach it seriously. That doesn't mean I don't want to have fun, but you know, not being glib about the challenges.
Well, for sure, you know, that's going to be very difficult, and I would say mostly for non-technical reasons, which is why I would suggest, or if I would be able to well, not lead, that's not a good word, but you know, my approach would be to start slowly, on small steps, and you know, take time to find a common common ground, rather than now just brush and try to coerce everything into a coherent vision that we can sell, if you know what I mean.
Right.
But obviously, there are other aspects of it. So that's how I see it.
Yeah. So being compassionate with each other and understanding where we are, and that's why I asked the question. It's really important that we do that. So we're doing that. So that's good.
So guys, again, me here. Okay, we are almost 45 minutes past our original scale. I have to say thanks to all of you. I think that these 2 days have been amazing. Not only because, and not only these 2 days, because we have been preparing all this stuff for quite some time. So this has been really nice to be able to work towards this, and that it resulted pretty well. And also that what I see is that there's a vision here in this group that is very well aligned, and that this will probably, we never know, but we could have success with this, and it looks like everybody here is pushing on the same direction. So it looks like we have good chances on success here. I created a PowerLang mailing list, other one. Maybe we can rename the one of the hackathon, or else just you join it. It's powerlang@googlegroups.com. I'm going to add it to the documentation. But what I see now is that we should keep trying to do things together. This was a good starting point, a great starting point for making the group bigger. And I think that we can continue working from there and making a small community to advance, to get whatever we want to do with Smalltalk, or whatever we want to use to get advancing, so that as a group we can get, as we said when we were planning, we can get further away. So I have no more words. I just wanted to thank you.
Yeah, thank you. Yes.
Thank you.
Well, it's wonderful. You know, my experience around COG since Clement left has been relatively isolated, and it is so refreshing to be in community. So it's thank you very, very much.
Yeah, I have the feeling when I'm working on B for Ocerna, I have this feeling that I am the only one left there working on VMs, and it's like I am the one who has to deal with all the problems. No matter what happens, I will be the only one that will have to fix the problems, and that's a very heavy weight.
Well, you and I should hang out sometime. I'd love to play guitar with you.
Yeah. We could also do some music sessions.
Yeah.
But what do you mean you feel like you are alone there working on VMs? You are alone there working on VMs.
Yeah, but
Just like you only feel like it. That's just what the fact is.
sometimes you forget. But then when a bad crash happens and they say, Pocho, you're going to have to deal with this customer and do some remote debugging. It's like, couldn't it be other one? No, it's got to be me. But well, it is what it is.
Yeah.
So guys,
thank you so much. It's been a pleasure sharing this time with you and listening you tell many interesting things and showing many amazing things. So thank you so much.
well, thank you for being here.
Yeah. Thank you.
Well, guys, I hope you have a good afternoon, and so let's keep in touch and try to make this continue moving. Thank you, all of you.